All right. Hello, hello. Let's go. We're continuing with Runic here. Okay, so yeah, I'm continuing with the IR thing here, and I'm just trying out structs right now, and I'm changing the call here to deal with structs instead of just pushing a bunch of stuff on the stack. Which, I mean, it works. Either way works good, you know. But structs will give us a more generic way of, I guess, yeah, having, the why we need structs. So anyway, so this is now a struct here. Now how that works is that structs have a number of fields, which are like just a list of values right now, and then you have this type which you would use to kind of know what the fields fields are. But basically, yeah, right now we know what type this is, so we know that it's a we know that it only has one field, and that field is the argv right now. So that's what's going on there. So the field, so this is argv now, basically. And the value, so this is argv value. All this is like the old code, so like everything below here, so I'm not sure what we're gonna keep there, but we'll probably maybe need to, yeah, we need to have a list of strings in the end at least. So I think this field, if we go to the compiler and check executable call context, so here's the struct type definition. So we have the name, and we have the fields, and we have one field called argv, and the type is a slice of slices. So yeah, so yeah, I also made the slices being able to like determine their size, because that's really all we need here. We need to know what the size is. I think we'll see if we need more, but we have the element size, and that's kind of like embedded in the type of the slice now. So the slice, before the slice was just, you know, a byte slice, but now you can have any element size slice by doing this. And so because that, then we know kind of that's the size of each element. Okay, and then we have this, I think, get slice, no, what is it called? Is it here? We have get slice, yeah. So this would take a slice value and try to get the data that it contains. So it would get, well, it only works from the read-only data right now. So this, we get this amount of data or bytes here, and yeah, this is the address, right? Yeah, but the thing is now that actually we need to get times the element size as well. And that would be the byte of the slice. So it wouldn't get us the actual type that we want. But don't really, yeah, let's just figure it out from this end here. Alright, so this would be a slice of slices. So I'm gonna say, first we want to get value. Let's get this slice here. So let's do get slice. Is that self? Yeah. Get slice, and the slice is argv value slice. Yeah. Hello, Polaris. Thank you. Have a nice day yourself. Alright, so now I got the slice in like bytes form, I guess. So I guess we would need to kind of loop through. Yeah, so we have all the individual slices, but we need to kind of deserialize them here. So so we would need to, well, now I think, yeah, let's make this array list here. Yeah, and then yeah, this is filling up the thing. So we basically, yeah, so we basically wanna to kind of do that. So we would know the length by looking at slice length. I think we want to get the I there. And yeah, that's the length. And then to get the slice, the inner slice as a byte thing, we would need value slice. Now that's all of the slice, so that would be I times argv value slice element length element size. This would be kind of like a generic procedure later, but alright, so we got the slices bytes. Now these are, wait, no, wait, oh yeah, so actually let's do this. Let's do start is argv value slice element size, and then end would be start plus argv value slice element size. So this would be start until end. There we go. So that is now our like, it's a slice, but it's like as bytes. So we need to kind of turn it into a slice here. So we'll get the arg slice is going to be, and this depends on how you turn it into bytes, but I think what we have is we have ir value deserial, well, it's gonna be slice deserialize. Oh, now let's just use this, and this is a slice. Well, no, this doesn't work anymore, actually. Now we need a deserialize on slice. Why don't we have that? That's the struct. which is this here? Value. Okay. Let's add that, but we need to have more information here, because yeah, we need the element size, so we need kind of like the struct type or the slice type kind of thing here. So we don't need tag, we need like the type info or whatever, which would be this, but actually it's just the U size. So this is the U size. I just call this element size here. And then okay, so basically it's kind of like, how do we turn this into, how do we serialize this? Well, we're just first we're serializing the location, and then element size and length. I guess element size doesn't need to be on the slice itself. It's part of the type, so we probably don't need to have it on the actual data itself. So maybe we can get rid of this, but hello Fahim Stash, the Dune man, what the hell? This time with audio. Yeah, I usually have audio. It was just that one time I didn't have audio for like 1 hour or whatever it was, if it's that what you mean. But anyway, so yeah, so now these here, like, so basically we just need to read the size amount of bytes from reader, and turn that into, so basically, yeah, so read, well, actually, let's do this. Let's do like location is equal to read, no, take struct location, you're using the melange theme. That's what it do, man. Like, okay, well, okay, I'm gonna be honest, I don't know anything about Dune except that there's spice and sandworms and like a fat man or something. I haven't seen any of the movies or I've not read any of the books or anything. Yeah, location and then element size. We already know element size, so really we don't actually need to like know this, but this would be like take int, and then we get the length, which is the spice is called melange. Okay, I see. Well, I liked the kind of like I like the I also like, I don't know, maybe I'm inclined to like deserty stuff, because when I used Vim years ago, I always chose the color scheme called desert, which I think it was like built in or something. Okay, so unused function parameter, yes. Oh, wait, we don't actually need to know the element size. Right, okay, well, let's just do this then. Okay, but then we don't need the special function. We could just use the value. Yeah, okay, I don't know what I was thinking there. we deserialize because this is kind of like a pointer, just like an advanced pointer. It has like the location, which is kind of like a pointer, and then it has like element size, which we don't really need here. Well, actually we do need it if we don't supply it here. Yeah, because we need to return something. Yeah. But if we embed it in the type or in the value itself, we don't need to like pass it here. But I guess we'd want to have it in the size itself. So actually, let's just not store the element size as part of the slice. But it could be nice to have in the struct that represents it because of convenience there. Yeah. So let's see. Now we will just return location is location. Element size is element size. Length is length. There we go. So that's the slice, the serialize function. Okay, and now we don't call value, we have to call struct. No, slice deserialize. And this would be well, it's argv value slice element size. Let's actually just pull that out here. It's gonna help with the generic thing later as well, and the reader. So we don't really have a reader right now, but we can just create one. So reader is gonna be standard IO reader fixed, and we have slices bytes is the buffer. There we go, and there's your reader. All right, so now we should have a slice, and because you like deserts. Yeah, well, as I said, I don't know anything about Dune, so it's not because like I'm a Dune fanboy that I chose this. It's I don't know. It's I don't know. I just like the theme. I just like this kind of colors, I guess. But that is to say, like, I don't have this on all of the things. Like if you open up like a bash file, it looks like this. It looks more like a, you know, green matrix thing. Yeah, I have a couple of different like you know, settings for different whatever. I would like to get into streaming code. What microphone are you using? Oh, streaming code, right. What microphone are you using? I'm using a Blue Yeti. Does it sound good? I got it like many years ago. And then it was kind of funny because I guess it's a very popular mic, but we didn't really know it back then. So it's kind of like an older model, I guess. I don't know. RG length, right. Oh yeah, but the length is RV value slice length. There we go. Okay. Right. So now this would be the one of the arguments, and then the arg itself is going to be self get data or slice arg slice. And now this is our actual, this is the actual slice or actual argument here. And now we can append it to our argument list. And as I'm doing this, I feel that okay, maybe this was a lot more steps than we had before. Like before, like now we're trying to use this more generic slice structure to kind of have a slice of slices, and we're iterating through the slice, grabbing out this the slice, the inner slice, and we are deserializing it into something we can work with, and then we are getting another, yeah, this is like a dereference here, and then we're building up this thing. But like before, everything was on the stack, like each argument was on the stack. It was way simpler actually, and I kind of like that more. For I was just trying to test this struct thing out, like we have these structs now, so but it turns out like it's easier, I guess, from if we compare, if we go to the IR compiler and we compare like compile call here, executable call. So if you compare this now to what it was before, I think it's easier, maybe, well, maybe not actually. But before we kind of we pushed the values on the stack and then we popped them here, and it was way easier for the evaluator. And now we kind of need to do a whole bunch of more steps here. But it's nice because I just wanted to test the structs out to see that, okay, well, and also these slices as well, to see, okay, how easy is it to work with them, and what do we need to actually get them in place here. That's kind of like, yeah, okay, cool, it sounds crisp. Well, that's great. Thank you for informing me. All right, so so let's see, let's just drive this home here. So we have argv. Now this is the list, so we'll just append assume capacity, the item, there we go. So now we have the list instead. So instead of like popping for a number of arguments, which is way easier than doing this, we are now storing it in a struct that is stored kind of like in, well, it's stored on the stack actually. It's stored on the stack, however, all the data is stored in, in the read-only memory, I think. Well, we'll see. It's gonna look a little bit weird. Also, each slice, each location, each pointer is like 48 bytes right now, and that's kind of funny. Okay, so now we've built this up again. So let's see. So we've got not a struct. Oh, not a struct. Oh, also, I think what we need is, I'm not sure about the deserialization part. Like when we create this here, the fields are allocated here, and then the fields, wait, what the hell is this? No, this isn't correct. No. What the hell? No, we only have one field. This is the args. This is the args. The fields are values, but they are going to be a slice, oh, okay, so actually we could compile this first. Yeah. So this part is where we gather all the things, but we should have like, okay, yeah, so this doesn't work. We need to, we have like fields, we have one slice with values in it, but now it's like in the language land. Before it was in kind of like compiler land, now it's in language land. So now the slice is well, actually this, okay, we need a ref. Actually, let's do like argv ref is going to be self new ref. The name is argv. Okay, and then we set that to be a slice with, oh shoot, oh, we need to allocate. Actually, we need to, oh man, there's so many steps here. Okay, so we need to like allocate. I mean, maybe I'll go back to using the for this part. I will probably go back to using the stack for this, but I just want to go through this to have like an example of how it is to work with the structs here, and to kind of go through each step to see that we can actually do it. Okay, so we need where. Where did we have like the alloc thing? Wait, was that an instruction? No. Yeah, it has to be an instruction. Actually, we can't add. No, we can add read-only memory here. However, all the things might not be like in read-only. But okay, well, the argument list. No, that doesn't make sense. Where's the instructions? Yeah, so I was thinking of adding like an allocation instruction that allocated like memory on kind of like a heap thing. Because we need that. We need to be able to have like some kind of dynamic data. I mean, we have the stack, but we can't really use this. Well, we can. I guess we can use the stack for this, but stack is so local, so you can't really use it to maybe create a struct that you pass around, you know. So we have to have some kind of like garbage collection and all that. But yeah, I will have to think about that a little bit. But yeah, so maybe this part, like creating a struct itself, we can do, but for this part it's like, well, each argument might be, we don't know the location. Right now we only support for like the read-only location. But yeah, I'm just gonna BRB 1 second here. I'll be right back. All right. Back. All right. So let's see. I mean, I guess for now we could store like we're gonna have to change it later. We could store like a read-only slice that points to the other things. So let's see, what do we have? We have like add slice, but that, yeah, okay, so that takes element size into account here now. Yeah, so we're adding a slice, and that's actually going to be the location there. So this would be args. All right, and the element size is a slice size, and then the data is oh yeah, we need the data. Oh yeah, we don't have it yet, so I guess this would be like in the end we create this one. Okay, so yeah, we create this in the end, presumably with some kind of args data, and then this field will be from location args. That's the slice of this location here. Oh, it's already a value. Okay, so we just pass in args here. Okay, that's the fields of the struct. Okay. Now before this, we have to create all the arguments. So this would actually have to move up here. So first we compile all the arguments, and we have to kind of store them in a temporary list. So we're gonna have to create the args temp here, which will be, I think it's a value, and this would be arguments length. Okay, so now we're saying args temp equals that. Okay, and okay, I don't know why we're going like backwards here. Wait, because the expression that we are getting here should be from left to right. Yeah, I think it's because of the, I think we went backwards because of the push, the stack thing, push and pop thing. Hello, Baby Yoda, welcome back. Thank you. You sound sick. Yeah, I don't know. I've got a little bit of a snivel going on. It's kind of weird. It's like every time I stream, it's I like get these snivels. Not sure why. But yeah, it's that time of the year, you know, there's a lot of sickness going around, and or colds and stuff. And I've been like up and down for I don't know how long right now. So, but otherwise I feel great. It's just a little bit of a snivel there. Okay, so we have the args temp here, and We're populating it, great. However, we don't need to do it like backwards. That's kind of weird right now. I think it's actually wrong as well. We add one instead, and this would be 1. Because this needs to be like +1 here, because we have like the executable is the first argument, you could say, and then these are the arguments after that. So we need to kind of have argument length +1 here, and we start at 1, and that's the things we get here. Now we should also have, where is the executable? Okay, so that comes in as a value here. So actually args temp 0 is the executable, right? So that now we should have everything in this args temp array at the end of this here, and then we will, yeah, we add the slice here. So the args data is basically gonna be, I guess, this. And then we have to kind of serialize. No, we don't. Wait, we don't serialize. Well, yeah, we do serialize. Yeah. I guess we serialize this array. So let's see. We're gonna have the slice, but we don't have a serialize function on here. So I will make this here. Let's do serialize. And we need to have a writer. I like this pattern here, because instead of like, you know, having a buffer or returning an allocated, it's so much nicer to have the writer, because it also it leaves you open to use whatever writer you want. If you want it to be allocating, if you want it to be just a stack based thing, or yeah, it could be anything. And it's really nice, because then you can do it in like a streaming way. You don't have to allocate everything up front. Yeah, it's a really nice pattern. And then this would return, well, it would return like an error void there. Okay. So if we're looking at deserialize, first we're taking a struct location, and then we're taking an int, which is the length. So to serialize this, we would do the same thing basically, but opposite. We would write a struct, and the struct is going to be self location. And then we write an int. There we go. Okay, now we have the serialize function. Now the values, I'm not sure if we have a serialize function here. Now we do. Yeah, and it seems to be all set up here. We would go into like the else here for slices. We would check if we have the serialize function, which we have, and then we just call it there. So yeah. Hello, Satchit 0007. What's up? Welcome. Which language? This is Zig. The language that I'm in right now to program my language is called Zig. And my language is called Runic. Like Zig, you can see here. This is the language here. Use of undeclared identifier args data. Right. So yeah, now we need to serialize the thing. Let's create a buffer. And we'll create a writer. Fixed buffer, and there you go. There's your writer, and now we can say that args data is going to be equal. Well, actually, this is going to be buffer writer buffered, and then we simply call what do we call? Actually, we call. Actually, I think we just. Hang on. So all of these are slices that need to be stored in another slice. So we actually need another slice on. Yeah, and that's what we're doing here. We're adding that slice there. But how do we populate it? I think, yeah, it's just gonna be bytes. Yeah. So we're just gonna loop through all of the args temp, and we're gonna say arg, which is a value, serialize with the writer. Okay, so then we should have everything serialized into this buffer here, and then we get out the actual buffered things by doing this. And we add that as a slice itself, which would be the final args. Also, we need to free this thing. Okay, and then yeah, so this would be the args value. So this is a slice containing all the slices, which are all the arguments, and then this is the fields that the struct is like has here. Okay, I think we got there. Well, let's see if it works. Field 0 is executable. No. Okay. Yeah, the field, there's only one field, it's the arguments. And then we're pushing, we're setting context to that, and then we're pushing that. So we're still using the stack here. We could now, technically, we could embed the call, the value of the struct into the call. So it would be more like a function call. Now it's more like we push it, like, yeah, we push it on the stack instead, and the call knows how to pop it from the stack. But yeah, anyway, let's see, let's wrap this up. Don't say that, Blue. Some people might still believe. Merry Christmas. Oh yeah, you need endian. Wait, what's happening here? Oh, right. There we go. I've never compiled this code here before, so that's why we get a whole bunch of errors now. Array literal requires address of... Oh, this is like an array. Okay, I don't really understand how this works. Because it's like... the array, it feels like the array is created in this scope here, and then we return it. This is where I don't understand the whole scope thing in Zig. When you use, like, arrays are the only thing that's weird. And also, like, yeah, if you create a variable here and you have an address to it, you know, this is copied, right? This is a parameter is copied, so the address of that would be just local to this scope, right? Otherwise it's invalidated. But then we like we do this as types, and then we deref that and return, so we get an array out. I guess what I don't understand is like when you return an array that is local to the scope, how does that work? Like, I don't know. Anyway, maybe it depends on if you return it like that, you will now we somehow have the array somehow. I don't know. Okay, but I guess, I mean, since this just works apparently, so I could just use this to turn it into a slice. Yo, baby Yoda. Alright. Q, not a struct. Alright, so where are these? Well, it's gonna be like right struct somewhere. What do you mean not a struct? It's a union. I mean, it's a union enum. Surely. What? House is cold. Yeah. It's starting to get cold here as well. I think we got our first snow like the day before we celebrate Christmas here. But not much snow right now. Wait, so there's no like right union enum? And this right struct only works for structs? This function is inline to avoid dead code in case endian is compile known matches. I mean, our endian does always match the native endian, so we could actually use this, I guess. It's just doing this. I guess read struct would also be like take struct. No, wait. Pointer cast. Okay. -25. Oh shoot. Canada, right? Yeah, we kind of live in like the sort of middle, but lower middle part, I guess you could say, of Sweden. What's the difference between @as and other typecasting? I mean, okay, so the way it works is kind of, you have to understand like the the way it works here. So basically, you have something called a result location or whatever, and it's kind of like this. So let's say you have like I equals 5. So here we wouldn't know what type 5 would be, but it's kind of inferred, and yeah, it's on the other platform, Baby Yoda, on YouTube. So comptime int is the inferred one, but if you say usize here, it will be usize, right? Okay. Now if we do like as usize, this would also be usize. So it's basically right. It's basically just like to know what type this expression is, you have to, like, to know what type this expression is, the 5 here, you can either use as to kind of force it to be some type that overlaps with the actual value here. So if you would put like a string here, it wouldn't work, right? Yeah, well, it wouldn't work anyway. So but the thing is, like, if you, let's say you want to return something here, return 5. Now that doesn't work because of course this is a void. But if it was something like, you know, usize, this would get that types, because we know what the result location is, which is this here. Now, if you have something like I is a usize equals 5, and then x is a, well, let's actually use like u32, and then I32 negative 5. So now you have like I and x here, right? Now if you want to add these together, it's gonna be kind of complicated, right? So because you have like I plus x, but that's that doesn't work because yeah, it's okay. That's a weird message here because x is of course an I32 and not a u32. But it's basically like, I think it's what it's trying to do is it's trying to, also it's kind of interesting, it knows what type it is because this is like negative 5, so it knows, it's like comptime known, so you get this weird message here. But you can't do this addition here because they are two different, you know, types here. So, and you can't really turn the I32 into U32. So this doesn't work. And I'm trying to figure out how to make this work here. But yeah, what you can do, yeah, actually we cast this to an I32. So let's actually do an int cast. So int cast is kind of like, it's, you know, you're just saying int cast, right? Int cast on I. So we don't know what type it will be. Like, what type will it cast into? Well, it depends on the context. It depends on the result location, right? So what is the result location here? Well, we don't really have one. We have this expression here. So it's part of this expression. Now this is an I32, but it doesn't know what type we want to cast this into. Now, you could make the argument that it could probably infer that the type would be the same as this x here, but really Zig doesn't really do that. Zig just says, hey, we don't know what the type is, so you have to cast it into as I32 here. And now it knows the thing. Yeah, and you could probably just, maybe you can do this, I don't know. Usually you have to like int cast, but depending on the types, depending on like how easy it is to convert from one to another, like this is probably easy, but it could truncate potentially, you know, the most significant bits here. So this isn't like always what you could do to kind of, you could use the truncate to say that, hey, we know that we want to truncate this, let's say, into an I32. yeah, so there's like a whole bunch of different ways you can do it, and basically it stems from the fact that when you're doing this auto, like let's say in C or C++ or whatever, you're doing these auto conversions everywhere, and sometimes it's like, I don't know, it kind of like hides the complexity behind it, and it hides the fact that you have to actually do work in order to convert something to something else. Sometimes you have to do it. Like sometimes it's just a matter of the yeah, just the type information. But yeah, this kind of everything about casting is like explicit, but there's some very small exceptions. I mean, if this was like 5, I'm not sure if this works now, but if this was 5, it seems to work, perhaps. Yeah. So, because it's comp time known, so it knows that this works. But if it wasn't comp time known, then we could do like actually, is this comp time known as well? I don't think so. So this would be like an int i32. So let's say we do like a random number. This should be, yeah, now you get an error because it's runtime known. So we don't know if we can do this or not, because we don't know if i32 well, it could overflow. I guess, you know, that's a runtime error, but yeah, it's a nice thing to catch, because then you could handle it in whatever way you need to. So kind of all of these things are like explicit. Yeah. So it's like, you know, it's a bit of, you could say like a lot of safety railings there. Introduces bugs, happened to me before. Yeah, exactly. So it's just a, you know, extremely explicit and safe way of working with those things. And it can be jarring when you first start out, because it's just like, yeah, there's a whole bunch of casting. But then you kind of learn, okay, well, either you keep everything the same type, or you kind of learn how to make these kind of transitions the least hurtful way imaginable. Yeah, I usually work with the same type. Usually you don't really actually do that. That's the thing. Like the casting, I actually never really encounter it unless it's very specific, and that's also kind of interesting. It's like, but then when it's explicit, you feel, oh shit, now we have to do a whole bunch of work here to get this working here. Especially from like floats to ints, or, well, the other way around is easy, but floats to ints, then you kind of you can decide, okay, do we want to floor it, do we want a ceiling, do we want a round, what do we actually want to do with this conversion here? And of course you can do that in other languages as well. It's just that in Zig it becomes really apparent that, okay, we need to handle the case. It's basically just, it's also the philosophy of handling these errors. The errors are well, this is I think this is a writer error. The errors, you know, it has to explicitly be handled. It's like everything needs to be handled. The switch cases, the exhaustive switch case, every switch, like if you have an exhaustive enum, you have to handle all the cases and so on. And I like that. I like those kind of things, especially the exhaustive switch case, because then it's like if you add another case, you would see everywhere where you need to add more handlers now. Don't struct again. Oh, right, now we're back here. Okay. So, this was kind of interesting to me. Like, you can just do a pointer cast from anything to a byte. Thing and do this to kind of make it into that. Like, there's a function called mem2bytes that you can use as well, or as bytes. Well, 2 bytes, which I think kind of does the same thing. But then you would have to do this, I guess. So this one is like, yeah, it's doing as bytes. It's just pointer cast. Oh, it does align cast as well. Okay. I don't know. Anyway, maybe. Yeah, the align thing is not sure. But let's do this. And then for deserialize, we would just say we're gonna take so we're gonna read a slide, or how was it? How did you do this? Take array. Yeah, maybe we just take array. And then the number of things is going to be well, it's going to be size, right? Yeah. And then we will do bytes as value. And that's the bytes. So now this should be that type. Okay. Comp time dereference requires analyzing a well-defined layout. Okay, so apparently there's something weird going on with the union enums. I'm not sure. What's the square bracket for? Sorry, where did you see that? In here? The thing here? This is an array. It's determining that the size of the, like, this is the inner part is the size of the array. Yes, it's static. It's comp time no. It's looking at the type of the value and then taking the size of that, and you get this array out. But apparently, it doesn't work for. This doesn't work for my union enum here. Okay, I'm just gonna try and Google this here. It's a static array of slice. Well, okay, so the slice is like a runtime known length. So the slice is a combination of a pointer and a length. in like the runtime value. So the runtime slice is a pointer and a length, while the array is basically only a pointer, or yeah, I guess it's a pointer, and but it's like a static length. I'm actually not sure if it's a pointer, like, because yeah, I actually rarely use arrays. I basically never use arrays because I just hate working with the arrays. Slices are much nicer. I'm basically only working with arrays if I want to do like a stack array buffer thing. Is typecasting safe on Zig? Not always. You can kind of force casting into something that might not be true. I mean, you can turn anything to an array of bytes, and then once you have an array of bytes, you can turn that into any type that you want. Comp time dereference. That's the thing also, comp time dereference. Yeah, it's this one here. It's like I'm trying to kind of get the size of location by doing this. Maybe I can just use size of instead. Yeah. Let's see. Where do I do that? It's location here. 2 bytes. Yeah, the size. Okay, this is kind of weird. This should just be like, I was trying to like make this into bytes and then take the length. Like there's a built-in size of. There you go. Yeah, so basically you see here we're taking an array of location size bytes, right, from a source, from a reader here. So we're getting a number of bytes out, and then we're just using this function to turn it into a location. But it might not be a location from the start. It might be something else. You know, it doesn't matter what it was. So yeah. Not always, but it's mostly safe if you're not doing things like this, where you don't know. Well, this is kind of unsafe though, what I'm doing here. Because this location, like the reader might not read a location here. It might read something else, you know. But if we do things in the correct order, then it should be good. Because I'm working with, you know, a compiled language here that has, like, we could embed the types into the values, but I don't want to do that. Maybe we'll do it later. I don't know. Okay, so we get this weird type out actually. What is this? Bytes as value return type. Given a pointer to an array of bytes, returns a pointer to a value of the specified type backed by those types, preserving pointer attributes. Okay. I'll get a pointer. Okay, so what I would like to do then is dereference this to get the actual location value. Because then it would copy it as well. Then we would copy the contents there. And now this relies on the fact that nothing here is like allocated or anything, so, or an array. This is a pointer, so it should just restore the pointer itself. It should all be good. Okay. What do we get here now? So right, so here's like we need to extend the errors here. So this is like a reader error, I think. I'm just putting it there so we see what it is. And then this is now, you can see here, end of stream read fail. So we need to add that to our error list. I'm not sure if this is a good way of doing it. Like, I would rather have specific errors connected here, but there's so many errors that could happen here. I guess this is like the main path of the program, so this would like have every other error, but you get these super long errors. So reader error. All right, there we go. So now we're out of compiler errors. Let's go to our thing here and let's run it, and we'll, of course we get some kind of error. Okay, and here we can see here's the data, and we just print it straight out here as like printable. And you can see kind of like, okay, before this, you know, we didn't have locations here. Now we have locations in here. Every location, which is kind of like a pointer, is stored as 48 bytes. And I guess maybe this is like alignment stuff here. I'm not sure. What is going on here? Okay. Well, or maybe it's something else. I don't know. But we get this, now we get like mixed with these, you know, binary data mixed with these strings here. And we got this type thing here, argv slice. Oh, it's 40 now. I wonder why that changed. I thought it was 48. So this is like this is like a slice. Actually, no, the location is not. Oh yeah, I removed the element type. That's right, or element size. The location is like 40 minus, I guess 8 bytes for usize. So 32 bytes. So a location is 32 bytes, which is a lot more than, you know, 8 bytes, which is like a pointer type. But it's just because we have a union enum and it can point to different things, and it requires more information there. Anyway, and then we have these instructions. The coloring here is kind of bad. I'm not sure what we'll do with that. Maybe we'll change it to markdown or something. No, I don't know. What could be a good thing here? I mean, we could C. All right, C works. Cool. Yo, Penguin, welcome back. All right, so we've got, well, first we have this echo hello here. So we've got, what is this? Yeah, we're making a ref, which is the context. So that's the struct. So this is the struct that we're kind of trying to create, and then we set that to a bunch of stuff. Well, I thought that we would have more things before that, though. And then we're pushing that. Okay, interesting. And you can see down here we don't get any output, which is, this is the output part. I mean, probably because there's some kind of error here. Here's the error when we try to call the first call here. Struct while location is active. Oh. Okay, yeah. So we need to dereference that struct. Oh yeah. Okay. Yeah. I mean, maybe we could. We could push the struct. It's. No. Wait. No. Yeah. Oh yeah, because there's no way of referring to the stack as a location. There's no way to do that, so we have to use a ref right now, unless we implement a way to talk about the stack as a location. Well, okay, let's just keep this here. Or we could also do this. We could change the call instruction to actually accept value instead. Wait, no, let's not do that. Because I think I'm gonna change it back to what it was before. I don't want to use this as, I don't want to have this struct thing because it's way more complicated than it has to be. It's better to use the stack here because, yeah. Anyway, what was the issue here? The location, right? Evaluator. So we're popping the struct. Now this is not a struct. This is actually a location. So this is the location, and then the context. Actually, we can do this. No, let's do this. Location, and then the context is going to be self-resolve address. No, resolve value. I think. Yeah. So this will dereference if it's a location, it will dereference. Yeah. There we go. Right. So now now we can say struct here. Okay. Let's see now. Okay, we got an error. I'm gonna change this actually. Let's open up the runtime, the runner thing here. Let's change this to C now. Okay. Whoops. Ah, okay, I guess it doesn't matter. Okay, we got a lot farther now. I think, or no, it just showed all the things. Okay, we get a lot more. No, we don't get a lot more instructions actually. It's about the same. It just felt long there. Okay, we still get an error at the first call here. So I'm confused because I thought that we would add a whole bunch. Well, actually, you know what? Maybe I'm not confused because the read-only memory is filled up during compilation, right? But we don't actually see that in the execution because it's already done. So this slice will be a slice that refers to a bunch of, well, it refers to a point in memory. Yeah. And then we have like two strings it refers to. We have like the echo and the hello. So those echo hello should be like together. You can see here. And then this part is the slice that refers to these strings here. Okay, and then we have the next thing is echo yes. This is the slice that refers to this location here. So a lot of information to just refer to those things there, but okay. So that's why also like it's probably a lot better to push it on the stack. It's less instructions, but yeah, I don't know. So that's actually one thing, or one bonus here. There's less instructions, I guess. Okay, well anyway, yeah, so the call here. So what is happening here? Index out of bounds. Index 3209. Okay. Okay. So I can kind of see what's going on. We kind of 3209. That should be able to be represented in a page. 272 in IR. Hello, Nuevo VR. What's up? Just used GPT to boilerplate it, save yourself a week. I did that, and I can tell you that I did not save myself a week. I would say like been there, done that actually. Yeah, in fact, it got so bad I had to take over and do things myself. So that's what I'm doing right now, which is more interesting anyways, because this is, you know, what I want to do. But yeah, it can help with some tasks, but making a whole project is not feasible right now, as far as I can understand. Like, sure, you can kind of work a lot to get the AI kind of working kind of well with a large project, maybe. But that's not what I think is interesting right now. Like, yeah. And that's, you have to put in a lot of work to get that working. So you don't even save yourself any work. It's like you're just delegating. Yeah, well, you're just like moving from one type of work to another type of work. So don't kid yourself with that. Like, it's good for certain tasks to do in the meantime, but like some boilerplate stuff. But yeah. And yeah, I already got like the foundation up, so I don't really need to do anything with that. Anyway, what is going on? So 232, yeah. Wait, was it 232? $272, okay. Right, so here how we do this is basically, yeah, okay, we don't do any checks here, so that's one thing. But the data, so basically, we probably do want to check, you know, I mean, the Zig has an implicit check here, so we don't really need to do that. We just need to make sure everything is good. So when we store this, that's the part. It's gonna be this slice, maybe. Don't have a logger here. Well, let's just log debug and adding data length. I'm just gonna add this here to see how much it is. Okay, well, that's not bad. And then we call this add data here, which adds data into the read-only data stuff. And we're allocating the data, which also, yeah, it finds like a page that's gonna be able to accommodate the length of the data here. And if the length is more than page size, we get an error. And we don't get that, of course, because the page size is like 4 kilobytes. and then most of the things was 80, so, and then we get, so maybe there's something wrong with this part when we're trying to get the slice. Yeah, it makes sense that it's 80 because length is 2 and the element size is 40. Yeah. So actually, let's do this. Let's do like let's do log data or get slice, and then I'm gonna do like any to show what the slice is. Okay, so here we're getting a slice. We can see, oh. Okay, this is the problem here. So 80 length, that's not correct. So this slice is stored wrong, I guess. Okay, we're ensuring that. Oh wait, okay, so it's taking like the length of the byte slice. Or wait. Location. Yeah, that just gives us the location, yeah. Which is not a slice. Yeah, so no. Add data. Gives us a location. Yeah, so wait, compile call. Where's the thing? It's here. This add slice here. This guy. This is wrong. The length, I'm taking like data length, which is the data of the bytes. We need to divide this by the element size. And it needs to divide exactly. So we're using div exact. See, another safety rail here. Div exact element size. There you go. Okay, we still don't get any output, but now where's the, did we still have the get size? So now this is correct here. Okay, you can see here that this is now correct, although why does it say 4 here? Length 5. What? Address 0. 4. Okay, that's not correct. File not found. Right. Why do we have 40 on there? You are 40. But why are the underlying things 40 as well? That should not be 40. Get slice. Yeah, that's the first slice, and then get slice, arg slice, element size. Oh, no, this should just be 1 here. There we go. Those slices are 1. Yeah. Yo, Dialog. What's up? Merry Christmas. Oh, excuse me. Oh, man. Okay. Yeah, it's going good. There you go. Now it works. We get all the output here. All right. So basic. So cool. So it's kind of like a test. I'm probably gonna go back to the stack-based thing for this particular thing. But now we have kind of proven that the structs sort of work here. Now we haven't tried to put a whole struct in the memory or like in kind of like a memory format. But at least the slices work now. The slices of slices work. So this whole thing here, this whole thing is a slice of slices, which points to these 2 strings here. So the first 40 bytes of this part, this is 80 bytes. So as you can see here, I think 80 to 90, what? Okay. Anyway, so this is like 80 bytes. The first 40 bytes refer to the first one, and the second 40 bytes refers to this one. So yeah. And I guess the same amount of memory would be used on the stack instead. Like if we change it to be stack based instead of now being like in read only memory. I guess. We could also put it in the instruction itself. No, we can't. Yes, we can. We could just put actually we could just put the slice of slices. Yeah, we could just put this part in the instruction. No, not the entire thing though. Actually, I think this is 40 plus, this is like 120 bytes, because we need 40 bytes for pointing to this, 40 bytes to pointing for this, and then 40 bytes pointing to the entire list of things as well. Yes, I'm starting to do the IR thing because I think it will become crucial at some point. I went over this a little bit last stream, I think, but the IR enables us to do a lot of things that it was becoming kind of cumbersome to do in the other thing that we have, which is basically, so the difference is now we should be able to, for one, we could create a debugger pretty easily because we already have a way to kind of step through. If we go to like the IR runner, and well, also we get all this information about the instructions and everything, but so we get like a flat list of instructions, so that's cool. And then we also like, yeah, we compile it, we run, which in turn calls a bunch of steps. So in theory, we could create a debugger that could kind of step through the program. And also what this enables us to do, since we can step through each instruction, it also enables us to do kind of like virtual threads, so that each pipeline can be stepped through simultaneously or in parallel as other things as well that's happening. So that's really cool, because then it allows us to, without creating, you know, threads like real threads, we could create virtual threads that will run, you know, a whole pipeline, all the pipes in parallel. Yeah, yeah, exactly. We can do optimizations as well. So I really enjoy making the IR because I've done a little bit of assembly code, so I can actually, you know, I can connect the dots a little bit. So it's kind of fun making your own like virtual computer with instructions and all the things that you would need here. Yeah, because we have like a read-only section here, a bunch of data, and then we have the list of instructions basically. Yeah. Green threads. I'm not sure if I know what that means. Is that green? Like, is that just virtual threads, or? I mean, what I mean by virtual threads is basically we just embed in our execution of the instructions. We also have like a number of threads. So we'd have like the main thread, and yeah, it's kind of like a virtual machine. Yeah. We would have like the main thread, which starts out just the main thread, and then whenever we encounter like something that needs a thread, like a pipeline for example, then we spin up, I guess we spin up a thread for each, either for each pipe or for each pipeline. I'm not sure exactly, but I mean technically maybe it's more generic if each pipe gets its own thread, which just spins through its thing. Thread schedule by VM runtime runners. Okay, yeah. So that's green threads. I guess it is that. Yeah, so that's really cool actually. So that like because doing the way that we did it in the other evaluator, which just took the AST and tried to evaluate, like for one, it just evaluates everything at once. So you can't really stop at any point and continue execution. So another good thing about this is also now we can support, for example, you're chugging through a function which spits out, all of a sudden it spits out a pipeline and you have to wait for that pipeline, you know. So then you can pause that function, run through the pipeline, which could also be connected to other pipelines. Like if you call a function and pipe it to something else, it should churn through the function and then spit out a pipeline. Then it should connect that pipeline to the rest of the other pipeline, you know. So it's kind of like we also need to support like pipelines being sort of disconnected in the middle somewhere and then connect some other pipe, but still keep the whole pipeline, you know, like the whole pipeline open. So yeah, yes, some little things to consider there. But yeah, it would enable us to do that more easily than we might have done with the AST, the whole AST just being evaluated at once. Because I was thinking like, okay, well, if we're gonna try to do it with the AST version, then we should be able to, we need actually to be able to step through or pause like a function and continue execution later. So we need some kind of stepping mechanism. And that was just natural to move into an IR because you get that for free basically. And it is kind of like another step, but the evaluator is way easier to build now with just calling the instructions like. But yeah, I'm saying it's way easier now, but it might be super hard to do some of the things that I want to do. I haven't really thought out everything yet. I know it should be possible to do everything that I want, but yeah. Whether it be separate processes like Erlang or actual OS threads or whatever. Right. Yeah, step debug. Well, yeah, exactly. Step debug and also step for like execution purposes. Like, yeah. Actually, we could kind of make that right now. Like, we could actually, you know, the context. We could add. Actually, we need one context for each thread, I think. Yeah, because each thread needs its own stack and everything. So, well, we might have a shared context and then thread context maybe. Because some of the things could be shared, like the read-only and labels and the types. As for members, you could then also make it possible to provide your own custom allocator. That's how far. Yeah, I think I need that actually. I need to have some kind of allocator and garbage collector, because when let's say for example we wanna, I mean, let's say we read something from another process, we would need to kind of allocate, right, for that. If for example you want to. So let's say you want to say, well, const equals echo hello. So now all of a sudden we need to allocate this. We need to allocate whatever, because we don't know how large this is. And you know, once we can, maybe this could become a compiled language, I don't know, but once we have like allocation, we could put that in the language itself, so you could allocate memory yourself if you want, maybe, I don't know. But yeah, we need some kind of mechanism to allocate and garbage collect and all that as well. I believe that's also what V8 does. Yeah, V8 has its own garbage collector, which is very apparent if you ever try to like profile some web page and you get these spikes of lag, which is the garbage collector that suddenly decides to, yeah, now let's dump a bunch of stuff. Let's go through everything and dump it. I'm just gonna refill my coffee, BRB. All right, I'm back. I had to make some new coffee. It was empty. Yeah, so I'm not sure how I'm gonna do it. Maybe, I don't know, RCs, or because I made an RC in Zig, which I'm using in this compiler, or I mean, yeah, in the other evaluator, I'm using RCs for different things. But I'm gonna try to kind of make things like in the language as much as possible, because that would be kind of cool. Then we could maybe, you know, make it into a compiled language as well. We'll see. It would be kind of cool to kind of make, and then you can make the language in itself. No, I don't think we'll ever get to that, but okay. Well, I'm not gonna think about threads right now, because that's probably gonna be way later. Although it's going to, you know, it's going to change how the things will work. But I would need that to kind of boil a little bit more, I think. Okay, so anyway, we have this working now, so that's great. And now the question is, do I want to go back on this? I mean, it's kind of polluting the read-only data here. I mean, yeah. It's either going to be in the read-only data or in the instruction set. Like, that's where the data is going to end up anyway. But the thing that we don't need when we do the stack-based thing instead of this is that we only need slices for these two. We don't need a slice for all of for the whole thing. We just have two slices, so and also a number. So we have the number of elements and the slices. So, or we could also optimize the location. We could optimize the pointer that would so it's like less data as well, maybe. And then you can kind of map the address. You can map like, okay, well, the first I don't know how many, like the read-only section is these things, and then the rest would be, I don't know, heap, and then you have stack as well. So that could be how we could do it as well. So you have like a pointer is just it's just a number, it's just a U size, and then you get like the first portion is the read-only, then we have the heap, and then the last part is the stack or something like that. I'm interested in a bash-like language. Love me some bash. All right, cool, fine wine. Well, if you see here, this is kind of how it looks right now. Although we don't really show everything here. I'm gonna show here's the MVP. So here's like, well, this is what worked before I started to make the IR version here. But this is how it worked before. It's kind of also this version is kind of slow, and I think I know why it's slow. I think it's because we're copying the entire env map before each call, so I think that's why it's slow here. But if we run this, you can see all of the output here, and I'm just gonna show this. Like, here's the MVP. So here's the bash version. Well, it's my bash version anyway. And I can do enable diff to see kind of what's happening. So here's like, okay, well, you know, this is an if now instead. We don't have like if then else phi. We have like, you know, programmer syntax, normal programming language syntax. I don't know. Well, I shouldn't say that. It's more like C. It's C based, I guess, more. Or well, it's zig based actually, if you want to be even more specific here. But yeah, we have like this if else. Of course, here's an if inline without blocks here. For loops is like the zig version here, so we have ranges, and then you capture I, and then and this is like a for loop with dynamic range, so you can, I mean, in zig you basically just replace the number here with a variable instead, and that's it. In bash, this is how I found out you could do it. I'm not a bash guru or anything, but you would have to kind of call another process to be able to generate this thing. You could probably do it in other ways, million ways as well, I'm not sure. Yeah, and the functions, since this language is going to be statically typed, so everything has like a type. If you don't see a type, it's because it's inferred from the value. So, but everything has a type and it's static. So this function has defined its standard input type, which is void, so it doesn't accept any standard input. And then you have parameters here, and then this is the standard out type. So the functions kind of work like, you know, it's like processes. So it's kind of like the same as bash, you know. This is how I kind of have it right now. So the functions are like, they don't return a value, they will return a kind of stream of values, and that's the standard out. So the thing is here that what's the difference going to be is like you can have typed standard out, standard in. Well, that's the hope at least. So you can have a typed standard out, standard in. So that means that you can stream, instead of string, you would stream like integers or structs or any type you want, basically. So yeah, kind of like you could turn it into type safe pipes. Okay, and then we have like you know, variable bindings here. I find it kind of interesting here. Like in zig, you would have const for a constant and var for a variable, or mutable, immutable, you know. But in bash, you don't actually, or well, you have to use the declare thing, and then use like -r for read only. Then you can actually have a read only variable, and I didn't know that before I did this here, but that's kind of interesting. And then and you can also well, here's like interpolation example here. You could use while I less than n and declare. Okay, I see. Okay, yeah, so that's another way you could do the range thing. Yeah, thank you for that. Up here, yeah. I don't know, I guess I was looking for like a for equivalent of ranges, but yeah, that works as well. And also, I'm gonna show also other things you can do with the for, like you can do other things. And here's like arithmetic in here is basically just, you know, you don't have to wrap it in a special double parentheses expression. You can just all the interpolations here are runic expressions. So, and that's the only kind of interpolation. Like there's no other kinds of interpolation or expression. It's just, you know, runic expression. So and it's built into the language. If you'd use a plus, you would get, you know, an integer plus another integer, just like in normal programming languages. And then you have like float is also, of course, like natively, I guess, supported here. While in bash, you would have to use something like BC to do it. But I mean, that's fine. As long as you know about it, it's fine, I guess. Yeah. it evaluates the expression in a separate shell, but also you have to have the double parentheses if you want to use like an arithmetic expression, because otherwise it won't do it. Like, yeah. Yeah, and here you can just say this straight up here, plus equals, and you don't have to have special, you don't have to kind of have this, you can have any kind of spacing you want. It doesn't care about your spacing. Didn't know about BC. Yeah, I didn't know either before I did this. It's kind of cool, and I don't want to learn Bash, but I kind of have to learn Bash now that I'm trying to replace it. So, because I need to know what kind of features, like I need to know how Bash works to make it like work kind of like Bash, but still not. Expression 2+1. Yeah, okay. I see. So there's a built-in or a program called that. I see. Okay, cool. Yeah. So, yeah. I mean, the difference is kind of like my language is going to be more like, well, it's kind of, it's taking it in and compiling it. I'm not sure what Bash is doing. I guess it's just executes line by line or something. I'm not sure. The pattern matching. Yeah. I am trying to add, I'm going to add pattern matching. I can show you, I have like in the to-do here some examples of how it might work. I do want to have pattern matching, but it's going to be later, possibly. So kind of something like this. Matching, and then this is like absolute match or whatever. It's like, okay, do we match this exact string? Maybe we can have some kind of glob expression that it matches this. So the thing is, this expression is either going to be the a type of value that this is, so then it's going to be an exact match, or it's going to be some kind of pattern matching function that accepts. So it's basically a function that takes the value and returns a bool. So it takes the input, and so this would produce a function basically that would take the input string and return a bool if it matches this. And then yeah, very useful for argument. Yeah, I know that the case thing is very specific. And there's like all these different kind of, the problem that I have with Bash basically is throughout the entire language or thing, every like feature has different syntax, it feels like. So that's what I'm trying to get away from, and trying to make it consistent throughout, and more like feel more like a programming language instead of like, I don't know, it feels like every feature is made by a different person or something like that. I don't know, maybe it is, but yeah. So so yeah, this would be like, either the value itself or a function that accepts the value and returns a bool. And here you have like the file pattern. Of course, you can pass in an identifier to this matcher over here, or you could have maybe a regex. We'll see if we can put regexes in here. I'm not sure. That feels like a daunting task, but it would be cool, just like in JavaScript, that you would have. Maybe we would even use no, but some kind of regex. Maybe there's, I'm not sure, there has to be some kind of regex library for Zig, or we could use some C library maybe. I don't know. Anyway, yeah, so that would be cool. And then the regex will basically just be a function that takes a string and returns a bool. And I know in some cases like regexes could be used, like in JavaScript for example, you can have like a regex isn't simply a function, it actually has some state on it as well, so that you can iterate over like a string, input string, like multiple times as well. So it has like some kind of internal state as well. We'll see what happens there, but because we're gonna have like closures in here, so it might be able to have that as well. This could be like, it could have like its own closure when you create it, and then it's kind of like a function with state. So yeah, anyway, yeah, that's a little bit of the pattern matching there. Okay, and I'm showing all this. I'm kind of using this as a or not a benchmark, but a kind of like a test suite to check that all these features are actually still working as well. So I'm including all of this, these expressions in here, plus equals. And I was actually surprised that Bash also had these. There are things in Bash that's not gonna exist in my language as well, which is like I don't think we're gonna have like plus plus or minus minus or anything like that. There's gonna be other ways to do the things you need to do, basically. Okay, we'll see. Maybe we need those, maybe not. We'll see. Okay, so this was also kind of interesting, like because the booleans, I actually now removed booleans from the language because they are replaced by another type. Could you guess which type we're talking about? JS also has a way of defining regular specials dynamically with new regex. Yeah, that is also, I'm not sure what we're gonna do with that. I mean, maybe behind the scenes, regex is actually, maybe you have a function that you call that actually produces a new regex, and that you can use that, or just use the regex expression directly. No, it's replaced by the exit status or exit code or whatever from a executable or a function. So a function also has, so when you have a function call, it will have two kind of results simultaneously. So it would have the normal like standard out result, and it would or any kind of number of pipes, actually output pipes, and then it would also have the exit code if it was successful or if it was some kind of error. And then also like the error types in Runic is not only, it's not gonna be always gonna be like the byte value. It could potentially be some kind of error value that has more information on it as well. Okay, so because in Bash, when you do things like this, like true and true, actually what you're talking about is kind of like exit status, because these true are actually number 0, which means success in exit code land, and false is actually 1. So it's kind of inverted if you're thinking about true and false in C, for example, where true is 1 and false is 0. And the way I had to do, so the way it works in Runic here is that we interpolate true and true, and I'm contemplating whether to change this to double ampersand, or if you can use both. I'm not sure. I think I'm leaning towards using double ampersand, but right now it looks like this. So you have true and true. This will of course produce a true, and then when we interpolate it, it's gonna coerce into a string with the value just 0, right? But in Bash that doesn't happen. If you just put this like this, this would not produce any output at all. You have to kind of output to standard out in order for this to do anything. So, or well, it does something behind the scenes, you could say. So we echo out the result here of the last kind of statement or execution or whatever, and that will produce the 0 or 1. So that's what you had to do there. And I had to, that took a while for me to figure out how to actually do this, but in the bash version. But yeah, in my language it's just going to be this. You're going to be able to coerce this into a string like this, and that's what's going to happen there. Okay. If it's just an exit code, like this value here is just an exit code. Like if you would call echo here, it would actually not use the exit code of echo and coerce that. It would use the standard out to coerce into the string. And here, actually, this is kind of interesting as well. So basically, here we're setting and table to the result of this. Now here we're using, like in bash, we're using a here doc, which basically is like a multi-line string, is this part here. And that's kind of nice, you know. I kind of like here docs. I'm not sure if we're actually gonna have here docs. Maybe we'd want to have here docs because of the way, you know, we want it to be like bash. But for now we don't have here docs. So what I did here was I took I bind a block of code or a block here, and since the block is like producing a bunch of standard out, we're just capturing all of that and putting it in this and table in memory here. And then we can use that to echo into pipe column here, which makes like a nice table layout for us here. Now, if we support, this is one of the things that IR will help us with, because we want to be able to support this instead. Like you could pipe the block directly into column blah blah blah, and that will actually set up this pipe so that first this will connect to the pipe and produce that. This end will keep open until all of these are done, and then we're done with that. So it becomes more like a streaming thing, because right now with this it's actually more like a synchronous thing. Like everything here needs to complete, and then we store it here and then put it in column. But now with this thing we actually step through this block and then step through the pipes like in these virtual threads that I'm imagining, and then it will be like a streaming thing instead. But we don't have support for that, so I had to do it like this instead. And then I did the equivalent in here as well. But I believe that we could probably pipe directly here into column in bash. So good on bash for that. Like it was actually way more complicated than I thought. Like these kind of you know, the pipelines and the streaming part especially. Like if it wasn't for the streaming part, it's extremely simple. You just wait for the process to end, you pass it through the next one, and so on. The streaming part is what makes it incredibly complex all of a sudden. How would you be able to choose between blocking and streaming? It depends on the context really. So in this context, it's always going to be blocking because you need the result to be stored in this value before you move on. If you want this to be streaming or like an async, you would do something like this. You would add this you know, the background thing. So this would be now an asynchronous result here. That's the plan anyways. I haven't gone into that part yet, and I'm not sure how it's gonna work, but that's the plan. So you're gonna be able to turn anything into an asynchronous, just like in bash where you put things in the background, a background process. You would add this thing to the end and it would make it into a background thing. Yeah. And all like these pipelines here, this is also like synchronous, like we execute this before we move on to the next part, right? So it's kind of like each statement is blocking, but the pipeline inside is streaming. That's the thing. But if you, and then, so this echo and this column will spin up simultaneously and it will stream through the data here. But then the whole statement will wait for this to for all of this to be done before it moves on to the next part. So that's how it works right now in the other evaluator that I have. Maybe it will be confusing with add if it also works for the same as background. Well, the reason for the add ampersand is because that's the same as in Bash. You would also put an ampersand at the end to make it into a background process. Because background would still need to finish execution technically. Yeah, so I think the way it's gonna work is, let's say we have this OR table there, and then instead of now in the actual language later, you would be able to like pipe this directly into column, and that will now become like the thing here. We would actually need to kind of wait for this because of this statement. If we put this statement in ampersand, it would also become a background process, and we continue on execution in parallel. But if we do this, now we have to wait for this. So now we're technically waiting. We're consuming both of these, this whole pipeline here, before we continue. So this would wait for this here. So it depends on how you use it now. And then also this would also be valid here if we remove the thing, and this now becomes an execution result, and then we pipe that into something else. This would like coerce this basically to a stream of bytes, which would pipe into here. So this would also work. But right now it doesn't. But that's the plan anyway. Yeah. So the pipes are the most. That's the most like advanced thing about this language, I think. That's the like the pain point of the language, like the pipes and the pipelines. And I haven't even gone to think about how that would work in the IR. The only thing I know that we're probably gonna move from the way that we did it before to thinking about how the pipes work in the operating system, and then try to mimic that as much as possible, because that will make it a lot easier to think about it. Like the pipes in basically the pipes in the operating system actually has like two connections, so it has like input and output. One second here. All right. Okay, and then we have these, arrays here, pretty simple. We just define this here. I'm not sure if like because I've seen arrays. I've seen this. If you want like in Bash, you could do like item in and then just state 1, 2, 3, and that would also work, I think. Yeah, that also works. So I'm not sure if that is a special syntax with the for range thing, or the for like expression here, or if you could say here like one. Well, actually, let's do this. Let's do my array 2 equals 1, 2, 3, and then this would be, I don't know, my array 2, because it would kind of expand, I guess. I don't know. No, wait, 2 command not found. Okay, what if we do that? That works. Okay, so it could be a string, and it would kind of expand here, I guess, to 1, 2, 3, and that would work as well. And I think what you can do is also, it's kind of weird, like in Bash, you have this special thing called like, what was it called? It was some kind of separation delimiter thing. I don't remember now what it was called, but you can set some kind of default delimiter to something else than space, like pipes, for example, and it would like use that as a delimiter as well, or instead. But anyway, so here you can see in Runic, or well, this is copying the zig syntax here. So basically, you have an array, and you just say for my array, and then you get the item out for the capture here, and then it works like that. Or you can have the block version here, which also includes like the example of multiple sources. So you would have my array and then a range with an open-ended end. So this range would match the length of this array, and so you would get like item and I out, and then use them separately. And I was actually surprised that it worked pretty well in Bash as well. However, technically here you can have any number of sources, so you can have multiple arrays. That's actually something that we want to create as another example here, where we have like my array 2 equals 4, 5, 6. Oops, not sure why I wrote size there. And then my array. So now we can have like my array and my array 2, and then we get like A and B, right? And then we can echo A and B, and that would create, well, that would loop through, and if we run this, we get an error. Where do we get an error? It's something with the parsing. Oh, it's the semicolon. Okay. Yeah, it doesn't report some of the parser errors right now, but we have like 1, 4, 2, 5, 3, 6, right? So you can put any number of things in here, and then you can add the index as well if you want. So get the index here, and there we go. Now you have the index. So 0, 1, 2 there. All right, Penguin. Now I'm not sure how to do this in Bash. I mean, you could copy this. We make another array, which is 4, 5. Actually, you don't have commas there, because that would be put into the string itself, which I encountered before. And then you have like 4i in this. I mean, I guess what you have to do here is you have to use the index. Actually, we have to use index anyway. Wait, how does this work? Oh, I see. This is like, wait, this is the length, maybe? Oh yeah, so this is like the length, I think, of the thing. So would you have to do something like this? Whoops. Comma, my array 2. Yeah. I think that's what you have to do there. I'm not sure. I mean, as I said, I'm not a bash guru. So, yeah. Anyway, that is that. Okay. So, I think for now we'll go back with the argv stuff. Maybe we'll try to make this easier to create actually. We have this list of expressions. Now, if we know that they are supposed to be slices, like we know the types, we could maybe make this a little bit easier. So we would do this part in a separate thing. So this would be like alloc we could also make it into a slice directly, but let's do like allocate values or expressions as values. Which would give us a bunch of values out. And of course, we get an allocation error. And we get the expressions. And then the source. Do we need the source here? No, I don't think so. Okay, we'll put this in here. And we can rename some of this stuff. So this is the, I guess, out of temp. No, this is, well, actually, let's just call this alloc values, I guess, or just values, or result, whatever. Okay, let's just return that. Now we don't free it here, we have to free it over here. So here we get the args temp is going to be try self alloc expressions as values, and then we okay, a little less complexity here. Well, we're hiding the complexity, I guess. Oh, I see. And also this, yeah, we need like one extra for the thing. How are we using this? We're just try org serialize. Wait, what is this? This doesn't go anywhere. No, oh yeah, it goes into here. Yeah. So we have like buffer W, we go into there. And Yeah, that's the thing. So we could potentially, yeah, we could just serialize the executable in there as well. Okay, cool. So actually, we don't do this. We don't do this. What is this iterator actually? Oh, it's the reverse it. Oh. Okay, we don't actually need the reverse iterator. We just, okay, let's just do a for loop here. For expressions. Expression. And we compile it. And we get the result. And we put the result in the thing. There we go. Easy peasy. And then new would be just expressions length. I guess if something goes wrong, we will free values. Okay, cool. Oh yeah, and then now we can actually use the same thing as you can do in the other language. In my language, you could use double for sources, and then the other one would be a pointer to the value itself, and then you would populate that with the thing. So there you go. No need for keeping an iterate like an index variable around to access with the index. You could just do this. Now they have to have the same length, so otherwise it will crash here, but they should have the same length. And oh, I see. So this is actually this, because we're compiling as well. All right. Actually, this is just compile a list of values. Actually, this is just compile expressions. Yeah. And then we get back a list of values. Yeah. Okay, so that's that. And then here we would do, first we would do like executable serialize into the buffer writer. There we go. Okay. So this part is kind of, this is about doing that. Now the problem here is that we can't really turn this into a function because of this thing here. Well, we can turn it if we supply a buffer from outside, I guess. But we can't create a buffer in a separate function and then return that buffer. I don't think you can do that. Because it will be put on the stack. The function ends, the stack pops. If it's an array like this, it's not, you can't return it from a function. I don't think so. Although you can return like a struct, but all the arrays are invalidated basically. Fields, args. That's a, what kind of function would this be? Well, this is making the executable thing. Let's just do that. Let's take this. Actually, you know what? Let's take a writer actually. So this would be alloc executable context, executable call context fields, and we get a writer So what we get is a list of values again. No, actually, we get the fields. No, we get a list of values. Yeah. And now you are actually just an allocator error. And we need the executable. We need the args. It's gonna be a list of values. And we need the rider. Oops. All right, so we're serializing the executable first. We're putting all the arguments and we're serializing those. And then we get field argv, or this is the argv. Yeah. There we go. Naming complete. Oh wait, this thing. No. Okay, so this is actually this error here. Okay, so now we should say try self alloc executable call executable args temp into the buffer writer. Actually, what the hell? Add slice buffered. Is this duping? Yeah, we're writing it in. So, okay. So actually we don't need to pass in the buffer here. We actually can create the buffer in here. Because the data that's stored in here is just gonna get put into here. Yeah. Okay. And you don't need to try when you return the last, or when you return an expression that can error, you don't need to try it. You can just return it directly. Okay. And this would give us the fields. And actually we don't need this rider here. Oh, now we need to go back to this. Okay. Just trying to make sense of the steps here a little bit, and yeah, generalize things a little bit. So the compile expression is really nice. That could be used potentially for other things as well. This one is very specific though for this, but it's nice to take it out into a separate function and create it there. Now we could probably make some kind of like generic thing for the structs, like any kind of struct. Like this field is very specific to this struct type that we have, because we know we only have one field and it's supposed to be, you know, argv. So, but we could potentially create something else that is more generic, hopefully. Maybe not, but yeah. Now, but this struct type is like internal, so it's not like you can create this struct type from within a Runic program. It's basically just a test now to use with the calls. Actually, maybe, man, I do want to change locations to be more pointer-like. That would be pretty awesome, actually. All right, let's remove this. Let's actually just remove this other part. We can recreate it other anyway. Okay, and then we set. So after all that, we actually set the thing. I think if this goes wrong, we have to deallocate fields. Okay. Let's see, set. Yeah, so then, and then we set the value of this ref to be the struct here, which is an executable call context struct, and here's the fields. And then we push that into source. But yeah, I guess we could do that. We could also change the call to take a pointer to the struct as well. Or a value that can either be a pointer to a struct or the struct itself. But here we're pushing it to the scope, it's fine. And then we return void. That's the result right now that we get from a executable call. That's gonna change later, but it's basically gonna be, I think the call itself would produce some kind of value that we can store. Yeah, I'm not sure how that's gonna work. Either we could push something on the stack from the call, maybe. We could push. We have to kind of, like, when we call and we want to store that somewhere, we need to actually allocate. We need some kind of allocation construct to do that. But right now we're doing this. Okay, let's just run this again to see that it works. And it works here, cool. And you can also see this runs extremely much faster than the other version because we're not pushing, we're not sending through, or we're not parsing all the environment variables and everything. Like the other has like way more machinery going on behind the scenes. So yeah. Let's see. Okay, so one thing that I want to do is I want to change the locations. Let's do it right now because I know this is what we're gonna have to do this anyway. So the location right now, I'm gonna change this to be just a, actually, yeah, I'm gonna change location to actually just be a number. And then we're gonna be able to map that number. So basically it's just a memory address, right? And then we're gonna be able to map that memory address to either the read-only part, the heap, or some other things, maybe, I don't know, and then the stack as well. So that's what's gonna happen there. I'm just gonna be here 1 second. All right. Okay, let's just do this. Let's change this to be... I guess it could be a struct that has the address and then a bunch of convenient functions, maybe. But for having like convenient functions, I think we would need to get, like, for example, the data, the read-only data right now, it has a get function with a length and then the page here, or the pages. And so this looks at the page and the address to get the thing. So that makes sense, you know. But this is kind of like a realized, I guess, location here. Welcome back, Penguin. And I'm not sure if we even gonna have scopes. Like I don't know. I don't know about this. The scope thing is like, yeah, I don't know about the scopes actually. Like it makes sense from a semantic standpoint, but in the kind of the compiled version of the language, like I'm not sure if it even makes sense to have scopes. I don't know, we could, like, if you refer to an identifier, I mean, we need some kind of, what we're gonna have probably is some kind of symbol table, but it's not gonna be the tree-like structure probably. It's probably gonna be, maybe, like, I don't know, man. I don't know actually. It's just that it's gonna be a symbol table. It's because right now the scopes are kind of like, it also contains like data. That's probably not gonna happen. Like the identifiers are gonna refer to maybe a location. I don't really know actually. Like right now we're using refs for basically internal variables that we can use as a location to set some data. So it's basically kind of like a stack variable almost that we, but basically that we can create from this magical, you know, compiler land, and not actually put into the, like as an instruction. Well, it is an instruction actually. You declare the ref and then you also can set the ref. So it's kind of like a stack, but it's like a separate from the stack, I guess you could say. So maybe we'll change the refs to actually be stack based later. Maybe we have to do that now if we're gonna change locations to be a pointer actually. But right now the refs are actually, it's kind of like it's just a number. Well, it's a number with a name, with a label, but the label is only used for debugging purposes. The number is used as an address in like the ref stack, you could say. Well, it's not really a stack, it's just a list. It's an array of refs that grows. It's a dynamic list. And then the refs are stored in the IR context here. So we have the refs, which is basically just a map from these index, this index to a value. So it's kind of like this magical memory land where you can just create anything basically. But and the stack is kind of the same thing because we're storing values here. We're not storing like, I don't know, we're storing different kinds of values. We're not storing super primitive things. We can store anything in here. But also to keep in mind, the values themselves are never like allocated or anything. They are always either a primitive value or it's a pointer to somewhere else that has the allocation. So you never need to kind of deinitialize a value or something like that. It always points to either the read-only data, or kind of like well, something in the refs, or the scope. Well, because this, well, we don't have the scope right now. So what I'm trying to figure out, like, okay, well, if we change location, like the number to be just a number, right? We have to map it somehow to these things. I mean, we could just map it. I mean, we could just add, like, you know, map address, and this would be the context, and then the address would be some kind of usize. And then we could get a value out, actually. We could get a value out right now. We could actually do that. We could get a page, a read-only data slice out. I'm not actually sure. What should we get? Maybe we get a location, actually. Because the location itself could refer to these things. Yeah, I guess we get a location out, and then we change all location, like all the addresses, to get a location. Yeah, we could do that. So the location is kind of like the internal representation of an address, and then the address itself is just a number. But now we need to know how to map this. I think what we're gonna do is we're gonna say if adder is less than read only data because this is like static size. I'm gonna say data length. Let's do like data size. So we return data dot length times. So we're just gonna say times the page size. Where is that? Oh, what the hell? 2A. I have this weird, like, fat fingers, and I accidentally create this file all the time. 2A. I'm not sure. Okay, it's when I press W and I accidentally hit the 2, I think. So, or something like that. I'm not sure. Yeah, now I accidentally pressed QA as well. Okay. Well, where is the page size? It's in compiler. That's weird. IR data. Oh. Let's actually move this to IR. Make it public. Actually, let's put it in data because that's where it should be. Or the location. No. Yes. No. Yes. Read only. Yeah, here. So here's the page size. There we go. And then over at the compiler, we would say read only page size instead. Okay, now this would be times the page size. So that, so we're just thinking like this, the last page might be not be fully. It might not be fully done.
I guess what we could do is say -1 to compact this a little bit. Because we should always have like one page at least. Otherwise, what are we doing? I guess if length is 0, we just return 0. Right. So then we know that we have -1 times that, except we need to do this because of the thing. And then we add the last. So if length is 1, this becomes 0 here. And then we add the last one here. Data length -1, length. Okay. So if we're within the length here, we will say, we will return data and I guess from adder we need as well now, so from adder okay, so how we return this from an. So basically what we're doing is we're trying to figure out which page are we talking about. So we're gonna say this, the page is gonna be, I think it's like div floor. Numerator is adder, denominator is IR read-only page size. That is our page, and then it's gonna be like init page, and then adder is gonna be adder mod. Let's just add at mod, I guess. Okay, that should work, right? Okay, so now we should have that. So now we can map an address like this to either the read-only here. So we're checking if adder is less than the data size. Maybe we should cache this. Nah. And then we will check if the thing is in data. We get the data address here. Otherwise, we check if it's less than. Well, now we need the data size, I think. Data size, whenever it says like data size, it's actually like read-only data size. Let's call this like data end. And then next thing would be the, I guess, the heap. I guess the refs could be stored on the heap then. Like they could be part of the heap, I guess. But we can't look at the ref length because, well, I guess this could actually be like a memory. We could actually check here for memory safety, actually. Like if you're referring to something that is actually an actual thing. But then we would have to check, we would have to go through each ref. Maybe we should have like stack start instead now. Stack start. Let's do math max int usize and minus, yeah, I don't know, stack size. So if we could also say stack start. So how, so U size is 32. Well, let's say it's like the minimum size of U size is 32-bit, right? So what would this be? Okay, actually, how much would we want the stack size to be? Let's do like, so this is kilobytes. This is 4 kilobytes. How large is the stack size of like a normal process? Standard stack size 10 megabytes per thread. 1 megabyte on Windows, okay. 10 megabytes. So that 10 megabytes is gonna be like this. How much is 2 to the power? How do you do it? 2. No. Is it 2? Well, is it power 232? Well, so it's like 9. Yeah, it's 4.3 billion. And this is millions, 10 millions. Yeah. So 4.3 gigabytes. Yeah, that's right. That's right. Okay, so then we got plenty of space. Because it's like, even if we say that, hey, we're using like a U size, so we got like 4.3 gigabytes, it's not that we require 4.3 gigabytes in memory to run a program. It's just that this represents the address, and then we're mapping it to the actual storage, which is nowhere near this size. So even if we have like a U size, like a 32-bit number for a, or a 64-bit number for an address, that doesn't mean that the whole space there is like used up or anything. Okay, so 10 megabytes. Okay, per thread. So actually, well, that tells me that this should be part. Well, yeah, yeah, because each stack is each stack is per thread, right? So, yeah. But yeah, and then because each stack is per thread, we don't need a separate space for each stack. This is kind of like a virtual address. It's virtual per thread, right? Yeah, that's what it is. It's a virtual thing. Okay. And basically what I mean here is like this, the address here is not like an app, like you take all the RAM of the computer and that's where you could have the memory. Like what it means is that we have a separate memory space that's a virtual memory space for each thread. and we're mapping each thing at the end here, each last 10 megabytes, we're mapping to the stack that is of that specific thread, which is in a different place. Yeah, it's kind of confusing here. I'm not really explaining it very well here, but anyway, so if this is more than or equal to the stack start, I think it's equal. Oh hey Vicent, my 29-day streak went to hell. Ah, sorry about that. You had like a 20. I saw you had like 25 last thing. 25, yeah, 9 days ago. Oh yeah, I totally forgot to. I forgot to check the notifications. Let's go. And Penguin, you had a 25 stream streak as well 5 days ago. Sheesh. All right. Why did you miss it? Was it because of the season, or would this be more than or equal to stack start? Let's say the U size is like 2 bytes. So we got 0 and 1. Stack size is 1. So that would start at 2 minus 1, which is 1, right? And the stack start, yeah, that should be 1 then. So yeah, that should be more than equal. Okay. So here we are going to say, well, this we don't really have. I don't think we have a stack pointer, so this is actually going to be pretty interesting. We're just going to say stack start minus adder. So yeah. Also, like a bonus here is like it's very easy to turn this into a location here. Okay, now we're in the stack region, so now we can enhance the location by introducing a stack pointer, and this is basically just going to be an address there into the stack there. It also means like between threads you can't refer to the stack, right? Yeah. Okay. Yeah. Sorry to hear that. I think I streamed a little bit on the night before the 24th, which for me, for my country, we actually celebrate Christmas on the 24th, which is different from a lot of other countries. I think there's a grouping thing going on. There's like certain groups of countries celebrate that. Actually, I don't know, but anyway. What? Huh? What? What am I missing here? What kind of syntax issue is this? Because it should not be a comma here. And there's dots there. There are dots there. This is closed. Maybe it's something up here. What the hell? What am I missing? Oh, there's something up here. There's something way over here. It's probably... No. What the hell? Yeah, there's something above here that's makes it weird, because these types are the wrong syntax here. So whenever you see this, something is wrong. It could be below as well. It could be below. Also, I'm gonna change you to a U size. What is going on? I didn't change much down here. It has to be something that I did just now, because this was working before. Ref. No. It has to be here. I just added this, but that wasn't the issue. What about this from address? Like if we remove this. There's some inconsistencies with the blocks, maybe. That seems correct. Data size. Yeah, here this is white, which is wrong. Like when I remove this changed the error here a little bit. But this is still white. What the hell? What am I not seeing? Expected after initializer. What? See how it changes. Oh! Oh my god. Wow, how can I miss that? Also, very strange. Yeah, okay. Man, okay, that was a lot. Yeah. Alright, so we got the stack. How do we represent the stack? Maybe with a super S. Capital S. Euro. Dollar. or whatever it's called. We have this one as well. I'm not sure what this is. Or like, why do I have like Norwegian? No, that doesn't work. I guess it's the this my keyboard has, like, if you have a Swedish keyboard, you're seeing you have like these letters here, O, and Ö. But on my keyboard, and usually it's only those, but on my keyboard I have like different ones as well. But that doesn't make sense. So maybe it's like, yeah, it's made for all of the countries. Anyway. Yeah, this is just S. Let's do this. Alright, see you later, Penguin. What sports is it? I don't think you ever answered that question, or I might have missed it. Okay, yeah. So now this, we have the stack start here. There we go. Okay. If it's not in the read-only or not the stack, we would have to assume that we need to look for a ref right now, or like, yeah, the heap, so to speak. So I guess this could be an error. Return refs, and well, actually, you know what? This is just a ref then. Yeah, ref equals adder. Well, actually, this will be data and. Whoops. Wrong convention. Sorry. No, I kind of live with this right now. I've been accustomed to using underscore for variable names. It does have its use. I've talked about this a little bit, but yeah. No, not data n. Yes, data n minus adder. Yeah, that should be that, right? So if data ends at, so wait, so if data size is 1, they should end at 1, right? So it ends at 1, which means 0 should be filled with the data and 1 should be the start of the next one. So and if this is 0 or this is 1, then that becomes 0. Yeah. Okay. All right. Now we have some more things here. So resolve value. This is basically like a deref here. It's kind of weird that we don't have for the data. I guess because we don't know what the type is. Yeah. And the stack. Well, the stack we could actually do. Stack is just items stack. There we go. And then we have this one. Set. Right, so we're trying to set a stack. So this would be kind of the same thing as the ref. We get the pointer. Well, here we can just say, I mean, this is gonna be an error anyway. So this is gonna be like self stack, well, context stack, items stack equals. So we can just do that. All right. Okay, now we can set stack as well. So that actually came with a really nice benefit here. Okay, so what we need to do now is we need to change all locations to be like this address instead. I'm gonna change the pointer to be this. Well, it's not a point. I guess it's an address. No, you know what? Let's just do this. Okay, so what do we need to do? We need to go in here. The location is actually not a location anymore. The location is actually going to be an address now, which we kind of have here, but I don't think this is used. It's only used like the initialize and format. Right, so I think what I will do is I'll remove location and we'll just keep address. And yeah, from location. So do we need this? Not sure. So this would now be, so this is the dereference here. So we get the address and actually we switch and then we get like context map adder. There we go. So now we get the same thing as this. There we go. What? Oh. Okay. Right. Oh, I see. This is not the same thing. Okay. Right. Oh yeah, this refers to, this is actually an instruction address, which is different as well. Oh shit. Maybe we need to map that as well, actually. I mean, yeah, it would be convenient. Yeah, this is kind of, this is like an address that's part of, it's part of an instruction is what this is. So it's kind of, this is kind of like an instruction address, actually. Instruction address. Yeah. And so it's not really the same thing. I think what we're gonna do is we're gonna change location to support instruction addresses. So we're gonna have like instruction. I'm gonna move this to outside. This file is becoming unreasonably large. I mean, it's only 500 lines, but yeah, it's a lot anyway. Okay, now all these are these things. There we go. Okay, so let's go to location And right, so now we have this here. Instruction, I guess. No, this is stupid. I don't know, man. I mean, we could do this instead. Thank you, Piano Coder. And this does have a format function, I believe. Yes. So let's use that. You can see here, like, there's different, like, I usually have only like the same character for each of these to make things convenient, and I don't have to think about what it's, and it's either going to be like S for state or whatever, or T for tag. So yeah, usually I do that. I didn't do it here, whatever. All right, now from location, well, let's do this first here. We'll figure this out. Key is a label key, okay. Is this the only error now? No, we have a bunch of errors now. Yeah, because I'm gonna wait with this because I'm not sure if we actually need this right now. We'll change you. All right, we had a bunch of these. Here we go. That's all of those. And what, we missed a whole bunch of these. What the hell? There we go. Okay. Set instruction. That's gonna be an error. Set instruction location. There's such a thing called like dynamic programming where you can actually change the program while it's running, but that's neither safe nor sane. So we're just gonna not support that. And I think it's actually possible right now. Like usually when you create a program, it has like a read-only section which is executable as well. But I think you can set it to writable as well, which means you can actually change the execution. I'm not sure if like modern operating if the modern operating systems do prevent that, but you could technically set the region to be writable and executable. I'm not sure if that's, you know, as I said, I'm not sure if that's stopped somehow in the thing, but yeah. Okay, so adder, right, so this, I'm gonna change you to be like instruction adder. Actually, no, what? That's part of the value, actually. So no, yeah. Actually, I'm gonna change you back to adder, and then this would be a usize. Make sense? Okay. Oh. Format. Oh. Okay, we're missing information here. we're gonna okay. So the refs no longer, we can no longer keep like the label. I guess we could get the label. Maybe. I'm gonna say this is like unknown. All right. Okay, resolve value instruction. Now, when is this gonna happen? So maybe when you have a pointer to a function or something like that. And what kind of value would that be? I mean, it's gonna be, I don't know, wait, an address to an instruction. What does that resolve to? That it doesn't really resolve to anything. I guess we could resolve it into the instruction location itself, the instruction address. But that would just be the value, right? That would just be... No, yeah. So maybe we do need this as a value. Let's just return it as the value itself. We'll deal with it later. Alright. Now we're back here. I think the compiler... I think the only address we're working with here are... No, because the slice and dice. The location here is actually not gonna be a location. It's gonna be an address. Or like, you know, a pointer. We'll create this as a usize. Okay, this is incredible now because it means that we don't actually... We don't deal with locations anymore. We actually just deal with two usize. There we go. Awesome. And then address is gonna be just 0 if we have empty, I guess. It's actually gonna point to the first read-only memory, which I guess it did before as well. Yeah. So whatever. It's gonna be the same thing anyway. Okay, and then the serialize. Now we don't do this. What we do is we just say the same thing. Usize, adder, endian. Okay. Right, it. And deserialize, we don't do all of this crap. We just say, well, this is actually the address. Take int usize endian. All right. An address. Now the address is interesting. I'm gonna write it as a hex here. So we don't get the nice formatted locations anymore, but we get this address instead, which needs to be mapped first in order to get that, but we can't map it because we don't have the context in the format function. But we could, I mean, you could add a point. I guess you could add a pointer here to the context, which would actually make us be able to do that. Or you could make a slice formatter that would have context on it to do that. So you can solve it in a number of different ways, but whatever. Okay, now, right, so when we add data, we actually get an address now. Or, I mean, we could get a location. I guess we could get a location that would then be turned into an address. Because the thing is, we don't actually know what the address will be here, because the data is still getting... No, we know what the address will be. Yeah, we know what the address will be. We just don't know what it will map into until the compilation is done. Hello, bad code guy. Another name. Stop being so self-demeaning. You are not talking today. Can you not hear me? My volume thing is showing on OBS, so I think you're supposed to hear me. Or maybe you're watching like previously when I didn't speak, when I was like BRBing or something. Actually, I need to refill my coffee. I'll be right back. Alright. Can you hear me now? I haven't changed anything, but maybe you turned up the volume or something. Okay. Okay, let's still, I guess we can still get the location here. We need to turn it into an address here though. Yeah. We need to turn it into an address. And in order to do that, we actually need the context, I think. So what do we need to turn it into an address? We need to kind of know what we need to know the size of the read-only data. You know what? This won't work. This won't work. Because let's say the data, like, let's say the read-only, like during compilation, the read-only data is growing. And let's say first we have like, well, you can safely refer to read-only data. So read-only data is safely turned into addresses because it will only like increase in storage. We could also set a maximum read-only data as well. We could set like, okay, well, if it's gonna be, we could set a region of data, like a region to be read-only data. So we could say like, well, you have like a maximum, I don't know, 10 megabytes of read-only data or something. I don't know. When will it get released in the market? What do you mean? You can look at you can go to the GitHub and look at it. It's open source basically. It has like a license on it, but I'm not sure what what that is doing, but yeah, it's doing something anyway. All right, so yeah, because the read-only data is only growing in size. However, if you're referring to like a reference, refs live between read-only and stack. Unless we make refs live at the end, like it lives like it grows from on top of the stack in the other direction. So stack would kind of have its own thing at the bottom. Wait, is that how they do stack? Like it lives like at the absolute end and then it decreases the pointer? I don't know. I always thought it was increasing the pointer. Now I'm pretty sure they have like a region of stack and then you like at the end. And then the start is like the end minus the size of the stack. And then it's increased. I don't know. Anyway. But refs could live at the start of the stack and then increase upwards. That would be kind of safe, I guess. But anyway, it lives between read-on. So if you create a ref, so a scenario here. If you create, let's just take the most simple thing. Create ref. This would be address 0 because there's no data in the read-only data. Like this is how this is a scenario of what I was thinking before. So this would become address 0, and then we add read-only data. That's also address 0. So already we get an issue here. But if we say that ref is like at the end of the stack, so this would be stack start minus ref's length. There you go. Actually minus 1 as well, because stack start has to be a stack pointer. So that could be the address of the ref actually. Yeah. Okay, that I think that solves the issue here. So when we kind of create the address of the ref, we don't. Yeah, because the refs go from 0 up. Maybe they should be like stack. Actually, this depends on how it's stored. Let's look at the 2IR context. The refs. Wait. Oh yeah, the refs are created in the code, that's right. And this is an auto array hash map with usize. So it means that it's both a list, but it's also mapping usize to like a thing. So it means that we don't, since we don't create it as an array, you don't access the number, like the element nth, number nth. You would access the key of usize. So it won't like grow to that Like if you put in a huge number here, it won't grow to that size. It would just create one entry with that size. So that's why it's like this. So that's good. That's perfect. So what we do is we will say yeah, we need some kind of function to turn this into an address. I guess we could have it here like self to address location to address location self compiler. We don't really need this to be a pointer. This would return a usize. All right, and then we return switch location. And if it's data, read-only data, we would just return data. I mean, it's really just gonna be like page times read-only page size plus the adder. So that's mapped directly. When will you continue with the game dev journey? Later. I don't know actually, but I will continue. So don't worry about that. I might do something. I might do things in parallel. Actually, I'm considering that. So I might do. It's just that my head is like filled with this right now, and I have to kind of start up. If I'm gonna do the other project as well, I'm gonna have to kind of start up that in my mind and trying to figure out where I'm going with it. And I haven't really done that yet. I'm currently thinking about this project now, but I will get back to it. So don't worry about that. I'm thinking of like doing it in parallel. So like maybe one day I'll do this and that next day I'll do that, or maybe weekly I will, like 1 week I'll work on this, next week I'll work on the game. We'll see, but something like that. I do want to kind of get back to it though. Yeah, thank you for asking. All right, so this will be all right. So we have all these cases here. Let's bring them in. Just curious. Okay. Yeah, great. Let's see. Ref is then so this so actually I think this is just a straight up ref dot. Actually, that's just ref. I think. Scope is like we don't support that, so I'm just gonna say it's. I'm just gonna say this is an error here. Unsupported address type. The stack is gonna be, I think it's just gonna be like the stack start. So IR, where is that? Is it now? It's context stack start, yeah, and then plus yeah, plus stack. That's right. And then instruction. This is going to be unsupported, I think. Yeah. So stack start plus stack. That's the the absolute address. We're kind of turning, we're turning the location to an absolute address of the thread, I should say. And so the read-only data is just straight up the same as it is, like it's data page times the page size plus the address of the page or the index of that page, and then ref is just straight up the ref dot counter. And actually, no, it's not the counter. Yeah, it is the counter. Yeah, it is the counter. Counter, it's a kind of weird name now. Actually, it should be like address. It should be address, actually. Yeah. Which is already absolute, so we should just keep that there. And self is unused, so I guess we could remove that. Yeah, turns out we don't actually need any context for that, so that's great. Expected use size found error. Oh, yeah, so I need to try that. Okay. All right, we have a bunch of issues. Still this one. Okay. Expected type. Oh, right. So this is an address. We need to map this. So let's say context map address. There we go. Fixed. Cool. All right. Let's check where this is called. So we have from value, from location. Yeah. From location. So basically, anytime we're trying to do from location here, we should do. No, we should do the to address actually. From location. Yeah. So actually, yeah, this would be address instead, and then we do to address location. Oh shit, we don't have that here. From location. Okay, so we don't really have this. So let's do from address, which just sets this here. So that's fine. And here we're gonna say from address now. No, wait. Yeah. From address. And then to address. There we go. Try. Set. Still works with locations. Actually, let's move this out. We'll just have it here as a convenience function. We could actually move it directly to location, actually. Yeah, let's just move it directly to location. That's way easier. To address. Why is this? Oh, right. All right, let's do that.
location error.
Okay. Location. So actually, now this is gonna be from address. And try. So this is gonna be location error. And this is actually it's location dot to address. There we go. Make it public. Right, and this would be lock to address. No. To address from address. We could make a special function here for like push location. Location is a location, and this would be push from address to location to address, and there we go. And now we can see here, we can do, where's the push? Here, push, and we can say push location, and we just pass this thing here. Here, push location. But that one is just a value. Okay, I guess that was it. Alright. Nothing name format in usize. Right, so this would be here. Format, I guess value. Format. Address. Doesn't have format, so it's gonna be, well, let's do address here. Print, let's do like X. Okay, yeah. The thing is, yeah, now the address is, it would be great if we could have a context here to format the things instead of having like, yeah, because now we don't really know where this address goes. Like we can read the value and try to calculate where it is, but it will be, it's nicer to have like, yeah, we see that it's a ref, or we see that it's a stack pointer, or we see that it's a read-only data pointer or something. But yeah, anyway. All right. Okay, that's all errors for now. I just want to see. Okay, so when we create when we set something, we're using locations here because the set instruction actually takes a location. It could also just take an address now. We could work with addresses here, although we don't really need to. But it will lower the instruction, you know, the instruction byte usage. but yeah, so we could change all of the instructions to just use addresses instead. We probably should do that. We don't really need to right now though. But yeah, let's see if this still works. Oh, we got a 1. Okay, interesting. So here you can see that the size drastically went down of the read-only here. Maybe we should say how large the data is. We could actually do that quite easily. Let's go to the runner and we'll say this amount of bytes, which is gonna be context read-only data size. There we go. $211 bytes. Great. Okay, so where are we going wrong here? Now we still see that in these functions, we still see these locations as they are here, basically. So that's good. But you know, we could still do that if we make the format function a little bit more fancy. But okay, so yeah, I guess this all looks good. We still have the same number of instructions. Of course, the first call we get some error, unsupported resolve value type. Okay. Evaluator, unsupported resolve value type. Data scope. So I'm gonna presume it's gonna be the data here. So we're getting an address that goes to the data, perhaps. So the only places we use this are the jumps and the call. Okay. What's going on here? So we get, well, okay, so this is the location. Let's see, so now we pushed a location which is now an address instead. So when we resolve it, it's supposed to go to this compile executable call. Right, so we're pushing this value onto the stack, which is actually, this is a ref location. So why does that not work? We get like data or scope for some reason. I'm gonna log here, pushing ref location, or let's actually do like push location. Well, no, pushing location into, so this maps into this, and so this would be the context dot, and it has to be a ref. And I'm gonna say I'm just gonna say the address here. Okay, we kind of know what the address is. I'm just gonna do this. Let's do Annie. And then, what was this? This was like location to address. Well, it's just 2 address. Yeah. Actually, we could. I think you can do this for an error type. All right, cool. Then we go here and we see what it becomes. Oh, pushing location. Okay, we see name. So address is 0. That is interesting. It should not be 0. Because the location that we're pushing is the struct, which is a ref. Location ref address 0. Yeah, the address is wrong. The address is wrong. New ref. Okay, yeah. Why was this not fixed? Do we have multiple refs? No? Well, I have only myself to blame here, but okay. So let's do like read only. No. Context dot stack start -1. So that's the start of the ref, and then this would actually go below. This would be like negative. There we go. Okay. There we go. Now we can see the address is like, okay, it's way up there now, which makes sense. And here's the actual address that we can see over here. Q, and yeah, it's supposed to be put like above the stack, so makes sense. And yeah, now we see all these huge numbers as well. We should probably put those in. We should put the things. Oh yeah, it's gonna be the format function of the ref. Let's use hex here. Yeah. Now we're starting to look like an actual compiled language with all these addresses everywhere. Okay. Which is kind of cool. I mean, we can actually like refer to address, like absolute addresses, which is nice. All right, so we got what's going on here, and yeah, I think, yeah, the call. Okay, we got a panic integer overflow. Data and minus adder. Oh, okay, yeah. So that map adder is wrong now. So actually this is just adder. That's just adder. Yeah. There we go. Now it works. Cool. Where did I put the debug logs? Everywhere, basically. IR evaluator, runner, compiler. There we go. Okay, cool. Now it works. Cool. All right. So we changed locations into just a U size now. So basically, well, they can be like translated back and forth between, like, I guess, a more informative internal storage of a pointer and also an absolute value. So that's kind of cool. So it reduced the amount of data that we're doing. Each pointer was like, or yeah, each pointer was like 32 bytes before, I think. Now it's only 8 in a 64-bit system. In a 32, it would be 4 bytes, I believe. We could also just use, you know, we could just use a 32-bit. Actually, it's kind of weird, like 4 billion. 4 billion should be... Actually, no, these are 64-bit. Yeah, this is 64-bit, I'm pretty sure. Because we have like 1, 2, 3, 4, 5, 6, 7, 8. So this would be a 32-bit here. We don't really need 64 bits, to be honest. Does your language have list node type? Like, do you mean like in the, like supported like natively in the language? Basic doesn't have much of anything right now. But I've just added kind of support for structs, like any kind of type of struct, but you can't really define a struct and create it right now. List node types, like what would that be? Do you mean like a dynamic array? Like an array that you can kind of append to, and or what does it, what kind of features would a list node have? I think we're gonna, are we just gonna change this to 32-bit? 4 gigabytes is gonna be, I mean, you don't need more memory than that. Right? It's not gonna be, you're not gonna make games or anything in this. You're not gonna make, I don't know. Anyway, let's just keep it like this, I guess. It's just a scripting language. It doesn't need more than 4 gigabytes in memory. But yeah, maybe, you know, Roland Dev, maybe we will try to, I'm gonna try and, like, if we get a kind of nice internal language for creating structs and defining functions and all that, you could potentially, you know, make that type into like a standard library thing. I foresee that's what's gonna happen. We're gonna have to support like allocating memory. It's gonna be like, it's probably, yeah, it's gonna have to be garbage collection, because you don't want to deal with manual memory management in a scripting language. That's gonna be too much. That's not the point of this. The point is not like optimization. The point is to just run some quick and dirty script that will do whatever you need it to do. Like the same reason why you would want to write a bash script is why you would want to write a runic script, just in a different flavor, basically. So you're not gonna be allocating memory yourself. The language is gonna garbage collect and allocate everything for you. Now for these strings here, they are actually allocated in a read-only storage because they are static. They are, you know, comp time known here. So, but right now I don't have support for actually doing something like this, like having some number being evaluated. When I have support for doing this, but not this. Like if we run this, maybe there's an error here because we don't support the type or something. Yes, okay. So n is like, it's kind of compiled, but it's not used. So I don't think, yeah, it doesn't end up anywhere. No, it's an if statement. This should actually end up somewhere. This should end up in... because now we should have more instructions. Yeah. So I wanted to make, you see, I have this like little script here in Vim, which makes, or NeoVim I should say, which makes like, I press a button, it runs the program, which we see this debug output. It would be cool if when you like highlighted a line here, it would jump to the instruction over here. But yeah, that was way too much for this little script there. But anyway, you can see the line number here, so we can search for the line number here. So we can search for like 3.1, and you would get to the thing there. So this is yeah, if result is a ref, but the ref is never used. It's basically set here, but then it's never used for anything else. If after we make, wait, yeah, that's another result. Oh yeah, but now we're on 6, so it's never used. So this could get like potentially optimized away, you know, if you have like an optimized thing. But if we start to use it here, we are going to see an issue because we don't have support for interpolating things, because we don't have a way to allocate. This would have to be allocated. I mean, technically we could make this, but since n is comp time known, basically, you know, you could make this expression comp time known, this would be comp time known, so this is also technically one comp time known, but we don't have that feature right now. So this would have to be like allocated, and it's also like we need to solve the allocation problem. We need to be able to allocate the string using these interpolation things and then put them together somehow. Now I'm not sure. I find the if without then a bit odd. This is how normal programming languages do it, except Lua. This is how normal programming languages do it. You have if, condition in parentheses, inline expressions like this. It's all perfectly normal. In passing concept, how would you know if without parentheses, if you had if condition? Yeah, so I had this issue before. I force the parentheses now because there's an issue, like this becomes an issue. This expression does not work without parentheses right now. I mean, we can add a then, but I don't want to add a then. I don't want to have to type then. No, I would rather have parentheses than a then. Because you can have blocks as well. You can do like blocks. And it looks stupid to have this. Okay, whatever. Laziness. It's just it's actually just it's what I'm used to, and it's also how Zig does it. Zig, and I'm copying the syntax of Zig here, so it makes total sense. Welcome back, Roland. All right. Anyway, only context where you want to be yet another copy. I mean, the whole purpose of this is to make a language that has consistent syntax with all the programming stuff, but then also mixed in with bash pipelines for like a natively supported, basically a first-class citizen almost. Like the executables, the executions are going to be the main thing in the language. So those are going to be, you know, pipelines and all that. And then the syntax, the rest of the syntax. So the pipelines are going to be like bash-like, But then everything else is basically, it's gonna be zig syntax. Forces grouping for if expressions. What do you mean? Yeah, it's zig. It's a zig-like syntax with bash mixed in, with bash pipelines. I just wanted to say that zig in Arabic literally means shitting as a verb. Oh, zig. That's funny. Zigzag. What does that mean? That's basically saying you know how it's valid everywhere. You know how it's valid elsewhere most of the time? We will be force you to do this instead, and if you don't like it, go as well. Huh? Forces grouping for if expressions. Like, I don't understand what that means. If with mandatory parentheses as a forced design flaw. Well, I wanted to do it without, but then it became difficult whenever you had inline expressions like this. Because we don't know where this expression ends. Unless you add a then here, but I don't... Oh my god. I don't want to have a then. Because it's not how zig... I mean, I'm copying the zig syntax, so it makes sense in that sense. You know? Grouping is tuples without commas. Just add a do or then keyword after. It's not how zig does it. Doesn't follow syntax that isn't even 1.0 yet. Be better than zig. Okay. I don't know. I you know, it depends on where you come from. Like, you obviously are used to Lua or I don't know, whatever language. I mean, Bash does it. What else? I mean, actually Haskell has then as well. But I'm trying to make the zig syntax here, which does not have then. So, I mean, I don't really care actually. But it's just that, okay, it doesn't make sense for me to force a then in there if I'm trying to copy the zig syntax because it doesn't have then. I mean, some things I am gonna change because, you know, Bash has this, and in Zig you would type and here, but I'm gonna change and to double ampersand, I'm pretty sure. TypeScript does not have then. Java, what are you talking about? You can keep it as a proposal. Java does not have then. JavaScript does not have then. C# does not have then. I don't know about the other ones. Okay. So then you shouldn't have a problem with this. I mean, I like it when you don't have to put parentheses. I like it. But it's also, you have to put then here now. And I don't like that. I mean, it's kind of, you know, it makes sense in an English reading standpoint. But I don't like to type them. I don't want to type them. I'm making a conscious decision on actually doing that. Almost all of them force syntax. OCaml, F# scale 3 down. Okay, so basically every language there that I'm not super familiar with. Yeah, it's a proposal. We'll draw the line there. It's a proposal. All right. Because people like to copy design flaws unless the whole parents are forced to parts. Before expression was an actual consistent design across other areas and had fundamental design differences. So other places where it's consistent is the for. You have parentheses here, the capture, and the block. Well, this is like optional, but that's another place where it's consistent. You have function calls, or not calls, but function definitions. You have, you know, fn type hello. You know, they're consistent here. It's consistent there. You know, there's all places where parentheses are forced. And like, what would you say for? Would you say like then or what? I don't like having these keywords. That's not necessary here. And you would have a different keyword for like for, do, or something like that. I don't like that. I don't like having these special keywords for these things. This without the keyword is consistent. You know. Yeah, it's just gonna how it's gonna be. You know, what about function signatures? Like, how would you would you put like, you don't force parentheses here. You would put like things in here somehow, and I don't know. For while loops, I use loop or do. Yeah, see, I don't want a bunch of that's what I don't want. I don't want these special keywords for each and every type of statement. Loop or do, thus the standalone keyword also becomes a loop keyword, like loop for infinites, do for in. Okay, well, I mean, to be honest, like, I don't really I don't really care too much about putting parentheses or not. It would be nice if you could miss it, like if you could not have it there, but it's not to the point where I have to add all these keywords everywhere. I don't want to have all these keywords. That's the main thing. This means you could also do loop stuff while condition, or do stuff while condition. Yeah, do while. I mean, we could have do while anyway. Like, you could have, but that would be very specific to just a do while loop. The thing is, like, the do while loops, I think it's zig, is like, I very, very rarely come across do while loops. I'm not sure if it's, I mean, zig doesn't even have do while loops, basically. Yeah. You want to be consistent. All right, dude. I mean, yeah, I'm for consistency. Like, I'm trying to replace bash with a more consistent language, and that's what I'm trying to do. I'm trying to use the zig syntax because I think the zig syntax is very consistent and it works really well. I like the syntax. That's why I'm trying to copy it. So that's that, basically. I don't think I'm not sure if we're gonna have, like, do while could be a proposal. You could argue on zig and consistent, but let's not. Okay. Well, I think it's I mean, I'm not saying it's all consistent. I'm saying it's mostly consistent. Like, I'm not saying it's consistent everywhere. Like, no language is like consistent everywhere. It's like, except maybe, I don't know, Lisp or something. I'm not that, but I don't like a bunch of parentheses everywhere. But But yeah, anyway, I just don't want to have different syntax for everything and have to look up, okay, how did you do this, how did you do that, and so on. It's for me personally, also, like, this language is not supposed to be, yeah, it's just like Zig, basically. Yeah. Anyway, except for one thing, and that is like the pipelines and the and or keywords are replaced with double ampersand and double pipes. Thank you, piano. Yeah. All right. Yeah. So. Yeah. So this fails. Unsupported callee. What? Unsupported callee. Oh, because of the N, maybe. Okay, yeah, this also goes into the scope a little bit, the scoping issue. Still thinking whether to go to symbols or keywords. When to keywords, because mathematically logical, not sometimes symbolically written as negate, or I'm gonna call it negate tilde or whatever. Bitwise not is also standard as this. Yeah, which causes ambiguity for semantic. Yeah. I mean, you also have the bang symbol, which I'm more familiar with, saying like not in logical. So opted for keywords for shorting, logical, symbols for bitwise. Yeah, that makes sense. And or not, like with for power, it's used for bit. Yeah, that also makes sense. Like star for power, I'm probably gonna use that as well, even though it looks, I kind of hate how it looks, but it's useful to have built in, especially for a scripting language. Like Zig doesn't really have it. I think, yeah, I mean, it does have the operator, but it's used for something entirely different. Like plus plus and star means something else. Both bitwise and non-shorting logicals. What do you mean by non-shorting logicals? Meanwhile, and or not are shorting. Oh, so you mean that if you have like and for logicals, like 1 ampersand, it would still run both, evaluate, like if it would evaluate both expressions. Okay. Okay. Same as in Ada, but with keywords. I don't think I've ever seen that. Non-shorting logicals. Interesting. Oh my god. And then Q. P or else Q. Okay. Well, I'm not trying to copy the English language. No. It's kind of cool. I've never seen non-shorting logicals in any language. I wonder how... That's how Ada does shorting logical. Oh, I see. I see. So, I mean, it kind of makes sense. Like P and then Q, that would be shorting, I would assume. Yeah, P or else Q. Yeah, shorting. Pascal does something similar. Okay. Well, I've never done any Ada or Pascal. Cool. All right. Yeah, that's interesting. Yeah, I guess now we would just, you know, evaluate it before and then store it in an identifier to more easily maybe. It does make sense. Are they lazily evaluated or no? Okay. What was I doing here? Unsupported callee. Why would we get that? Probably compile identifier. That would look up the thing in the scope, which we don't really have. So we don't have this in the scope. We have like compile binding, which should put it in the scope. Yeah, we're declaring that. So it should be in the scope. And then we compile the identifier. We look up the thing. We should get the bind. Well, we should get the result out. And what are we doing then? Call. Oh yeah, that's right. Wait, is it a call? Yeah, it is a call, right? So it's a call. So basically what's gonna happen is if we get a slice, we treat it as an executable. If we get anything else, I guess it's gonna be the value itself. So here is where we could have maybe a function reference that we call. But I don't think we actually have that right now. I guess if it's an address, it could be like a pointer to a function, maybe. Hello, Discordianism. Just dropped in to see what condition my condition was in. What is your condition? Okay, let's just say, I guess if it's any of these, we just return that. From value. No, not slice. Okay, let's do that. Actually, you know what? Void is void is probably not a supported callee expression. The struct is not really a callee either. You can't call a struct. And I guess the U integer is not that either. Wait, so what is the thing? It's an address, maybe? Wait. No. Yeah, we're declaring it to what? We're declaring it to... We're declaring this to a number. Oh, yeah. What the hell am I doing here? No, yeah, it's just gonna be the value. We're just gonna do this. Yeah. We're not the whole point here is we're not calling it. We are actually just producing the value that it is. So that's why, because all identifiers are turned into calls because of how kind of like how the language works right now. Is basically not a bug, but it's basically an unimplemented feature right now that we don't have the semantics to know if an identifier is an executable or if it's not an executable. I'm thinking about making executables explicitly defined so that you would have to define which executables you're gonna need for the script, so that we would avoid problems like typos, calling the wrong executable or something like that. And also it would help very much in the semantics of the language, of the compiled language, so we would know that if a value is actually, or an identifier is actually an executable, or if it's something else, or if it's something that does not exist, then you get an undefined, or you get an undeclared error for that identifier instead. And then we could have something like, okay, well, let's say, okay, well, what about productivity? Like you would want to declare, you wouldn't want to have to declare all the executables you need. So let's say you start to write the scripts, we could incorporate it in the LSP to say that, hey, this identifier doesn't exist. Is it an executable? And then in that case, you could add a code action that would kind of automatically sort of quote unquote import that executable for you. So that could be something we could do to solve that issue or compromise a little bit. But I'm not sure if we're gonna do that or not. We'll see. All right, so let's return like this instead. There we go. All right. Let's handle all possibilities. What are we missing? I think we're missing address. Okay, so I guess address would be the only thing we don't support, maybe, or actually we can't. We should support address. Yeah. It's just if it's an address, it might be maybe a function call. Maybe no, that could be its own type actually here. I'm not sure. Anyway. Okay. Yeah, the functions. Actually, the functions could have their own table. Okay, I haven't gotten to the functions yet, but now this is probably returning something else error. Okay, so we get this thing here. Yes. Do we have? So what is this? This is line 4. Okay. Whoops, did I see? Alright, this is line 4. So we call executable. Wait. No. Yeah. Alright, so yeah, okay. Here is the line 3. Here's line 3, yeah. So we have the result. And we set the result to 0 there. We set the result to 1 there. But the result is not really used. It's supposed to be bound in the scope, but that's not really happening. Yeah, it's not really stored anywhere. Like, how would we even get to the value? I'm still not sure what to do with the scopes, actually. Like this n here, where would it be stored? Right now it's we're kind of using the same like tree-like scope structure. But then when we actually execute the code, where would it be stored? Would we store it in like a flat, like a hash table with the name being very specific to where you are in the code? Maybe, I'm not sure. Because right now we don't have a where to store it. Also, you know what? The string interpolation, maybe we could make some sort of streaming thing there. Actually, yeah, we could create a slice of these, store it in read-only, have some kind of representation of the... No, because... Yeah, no, no, this compiles to... Actually, this should be like an identifier lookup of this, right? Or... No, it just takes the location of this, yeah. Push 2D. What? String result. Right. This is the now we're trying to do the string literal thing. So we have a string result. We set it to some. Yeah. It's basically we're just setting. Wait, we're setting the location to empty, I guess. We set it to like a read-only thing, which doesn't make sense right now, but we're just setting it to something. And then we're pushing 2D. What the hell does that mean? We're pushing this location. And that was... No, wait, now we're on the... Okay. No, this is the context, I think. This is the context of the call. I think. Maybe. No, it's not. This is the context. So what the hell is this? It's up here. Yeah, this ref, the if result on line 3, right? I mean, that makes sense. Okay, I'm also realizing that this is not scalable, right? The refs are basically, they are never like removed. So the ref counter is kind of like a global stack right now. We never pop a ref off that stack. So I think in the future we'll probably change the refs to be on the stack instead. But then you can't return it. You can't return it from the thing. Yeah, I would have to think about this a little bit. Maybe I'm not sure. Yeah, it's part of the garbage collection thing, I think. Okay, what is this push 2D? And then we're pushing that. Where does that come from? I think it's the, maybe it's the string literal. What is happening here? Because this is not fully implemented yet. This part is not implemented here. Oh yeah, we're pushing a bunch of stuff. Okay. And then we're not really doing anything with it. So this is unimplemented right now. It's like, okay, we're pushing... I guess this was the 2D, maybe, I'm not sure. text location is it's supposed to be the read-only address, I guess. Now this is, I think, the first text here. We get two things. We get a text which is empty, and then we get, because if you only have like one interpolation right now, you get like an empty text, and then you get the interpolation that we push the result of the expression in here, and that in turn is going to be compiled into an identifier, and then we do the lookup thing, which returns the thing. So this would be a call, and that's what we're pushing here. We're pushing the call in there. Is that what the 2D is? Why the hell would that be 2D? Push format, push. Oh no, the push, the value is a call. The format of that is what? It's just a tag. So why is that not the tag? No, maybe it's okay. Hang on, I'm missing something here. We're compiling the thing, the identifier. This should become a call here. Well, no, actually, we're compiling the call, right? We're compiling the call, and then we're taking, and then it's an integer, I think. Or it's a ref, actually, it's a ref to the integer, right? So it's an address. Oh, and that's why it's like on the read-only thing, perhaps. Right. Because the one, okay. Because these two, I think they are stored on the read-only data. So this is actually stored as a reference to one of these in the data. So this is stored as a reference to the read-only data table that points to either 1 or 0. And then when we call it here, this gets evaluated into the address. And then we have to kind of, I think we have to like dereference the address to get it. Right, that's what's happening with the 2D. The 2D is the address, I think, yeah. Okay. Right. Actually, you know what? We could format the address. We could actually do like from. Isn't there a from address that doesn't really require anything? It doesn't require. But that's the data. Yeah, we have map address. That does require the context, right? Okay. I was thinking like if we could do it here, we could kind of map it to some address. We could do it if we set an absolute limit to the read-only data. Then we could map it to something there, but whatever. Okay, but it's still the issue of how to actually construct this string. That's the issue also that we have. Is the how do we construct the string? So we have compile string. Now the idea here is that we would have this ref that points to the result at the end, and for some reason I'm setting it here, which is not really necessary right now because we don't really have anything to set it with, but we could potentially allocate things here. What we really need is like an allocating writer or something like that in the language, but we don't really have that. So and also maybe the result will be, maybe we could build that into the language actually to have like a stream, but then we would, how would that work though? Like each expression needs to be evaluated and stored somewhere, or compile, I mean. And then we would have like a slice of those values that then we would be able to use, perhaps. Yeah, I think that's the idea here, where we push a bunch of stuff to the stack, and that's the string literal. But the problem is we don't really know if it's a string literal that we are compiling. We just know it's an expression that we're compiling, and if it happens to be a string literal, we just push a bunch of stuff. That doesn't really work. I think I tried to use this as an intermediate thing. We're pushing all the things, and then we can go through each one to kind of build up the string from there, maybe. We don't, okay. Okay, we need to figure out this a little bit. I'm gonna be away 1 second here. All right. So, how do we deal with these strings? could we avoid an allocator actually? I mean, for now, we're kind of putting the things that are compiled, like the text are already, like they are stored in the read-only. So the text parts are stored in read-only, so those could be just used directly. And then we have the interpolation result is some, well, yeah, that's compiled directly here. So that is, you can think of it as before we kind of have the full string results, we're also compiling, we're also like executing each interpolation in order, storing the result somewhere. Like, well, this is, it's storing somewhere depending on the expression. It could be in literal that's stored in read-only data. It could be some kind of execution that like it could be a call to an executable, which we actually get a void at this point, but we're gonna change that later to actually get the execution result. But it could potentially be anything, and then we get the kind of the result here as a location on where that result is stored. So it could be in the read-only data. It could be in this result is it says a value here. It could be a literal value as well, and not a location, but yeah, it could be anything. Could be like an if expression and so on. And man, the idea I had before was like, what if we create like a list of all these expressions, all these like results, store them in a list, and then create a new type of value that is basically like a stream of strings or a stream of values that you could then use to, when we actually need to call the executable, we look at all the arguments, and we're looking at the type of the arguments. If the type is just a slice, we just interpret that as just a literal string. If it's a slice of, or if it's a stream, I guess that could be a slice of strings as well, or a slice of values. Each value needs to be converted to a string. So we kind of need this string coercion going on there, actually. So what we then could do, I mean, let's just try that, because I think streams of values are going to be so integral that it could be a thing that's just built into the language as a data type. But we could also in the future make it into like a struct to make it more generic, so you can kind of, I don't know. Anyway, yeah, so this would be like a value, and this would be, I don't know, a stream. And it's basically going to be a stream of, it's basically going to be like this value list. Well, this is like a buffered stream though. It could be yeah, let's just do that. Well, okay, so now actually we do need to like free that, I guess. Yeah, compile call. There we go. And we probably have like some format function or something here. So if it's a stream, we're just gonna say it's a stream. There you go. Okay. No more errors. Sure. Okay, so compile string. Let's create this stream here. No. And we know how many it's gonna be. Also, this is gonna be a value, and this is gonna be string literal segments length. So that's the number of things there. We would return actually now from value stream. Okay. I was like, no errors. That's weird. Okay, so we don't need this string result ref anymore. Yeah, it should be. That should have been an error actually, or maybe not actually, because we were using results here. Okay. Well, anyway. So we get the stream. Instead of pushing this, we need to set u to this. Actually, we can just do that here directly. There we go. So we just set u to the value that we get here. Actually, this is a location. So from location, there we go. And same thing here, stream I equals that. Should be the result, so we have to do like dot value. Okay. So now every entry is a value. Alright, cool. So that is now the thing. So now we're not pushing things on the stack anymore. We are just compiling the thing. We don't have a source, that's right. No member name from, oh yeah, it's from address, that's right. And then this is address, this is to address, there we go. Which we also need to try as well. And I really want to, like the source. I guess since we don't have any instructions here, it's just gonna be, well, this is the only thing that has the instruction, I guess. Yeah, okay. So I guess we don't have a source here anymore. So that's fine. And then you don't exist anymore. Okay. Fine. And the source is basically from which expression was this instruction added, so that we kind of track, you know, it's a kind of like a source map where you would map each line of code to the instruction that it produced. All right. And I just realized that we could potentially provide a source here, like an optional source in compile expression, but whatever. Okay, so now we should have a stream thing there. So let's go to our evaluator, and then actually, okay, so now when we build the argument list here, we go through each slice. Now before this, we can assume that the slice is always going to be a string. So we're just saying that, hey, I want you to read this as a slice, a byte string, a byte slice. But now it could be a stream or a string. So, yeah. Hello, Babinski. Did I say that correctly? I feel like I messed that up. Welcome. We could make the arguments themselves a stream now as well. So how would that, the issue now is like, how would we know if it's a stream or yeah, because the slice can only have one type. I guess if this was a problem in Zig, you would solve it by doing like a union enum. You created a website for a game. I could have sent to you, get your honest opinion. Sure. I'm not sure how valuable my opinion would be, but I can give it a shot. All right. So be bluntly, I'm trying to compete with Pokemon Go. So do you want me to comment the website or the game itself? Because right now I'm seeing like a bunch of broken image links. And is it Have you looked at, does it work for you, or have you looked at the site recently? Like some of the images work, but some of them don't. Okay. Avail.png gets 404 for me. Resize. Is it something with the resize thing? It says like query parameter resize equals 1024. Something 347 something. SSL equals 1. What kind of what kind of framework are you using? A WordPress, okay. Well, I'm not a WordPress expert. I've never used WordPress, basically. The only thing I know is that they use like PHP or something, and but yeah, I would start to try to figure out how to fix those images. And another thing is the website is not really, well, it's kind of responsive. But if you, well, okay. Yeah, it is responsive if you kind of launch the site with a specific size. But if you're trying to resize the thing, whenever you try to resize it, like everything breaks. How the art looks, okay. Yeah, I think it's look good actually. I really like those, the monsters that you can see like at the start. Well, can I show it to on the stream? I mean, I guess you're sending the links here, so yeah, look at this. I mean, it looks like Pokemon, of course, but different. So from this screenshot here, I'm not sure, it looks a little bit bare bones. Are these lines supposed to be here, or is that like an aesthetic thing? So GPS, oh, I see. Oh yeah, Pokemon Go, that's right. The lines are roads. Oh, I see. Okay, cool. Yeah, I mean, I really like this this pixel art. This looks really cool. I like this cat with the sunglasses here and the suit. And this looks kind of like a duck fire thing. But what is this? This doesn't look like the same game. Now, I get all these issues here. So your other game. Oh, okay. So this is the thing, or... Or is this another game? Attack on Titan, Earthbound. Oh, is this like, okay, so these below here is not another game? I see. And then this is like the Pokemon thing. Spirit links. Okay, cool. Yeah, I mean, art-wise, like I really like it. So so there we go. And of course, you know, Pokemon Go has proved itself to. I mean, it did. I'm not sure what the popularity right now. How many are still playing it? Do you know? Hopefully, I can single-handedly beat the Pokemon Go company by myself. I hope so, man. Good luck. Still really popular? Okay. Yeah, but then you have a market. Do you know how many like those kind of games are out there? Like are there many Go like games or whatever it's called? Like what is the genre called? Is it called like Go? It's rare because they're hard to code. Okay. It's augmented reality games. I see. Is it really augmented reality? Like, I thought it would just it was just like you go to a place and you would get this battle on the screen. You don't really like move the camera to see Pokemon, or what? Is it really augmented reality, or is it just, you know, you're just seeing the GPS location? Because it's rare, it means I'm the only one that has stored inside a GPS game. Huh, okay, that's kind of cool. Which is why I'm optimistic that I can succeed. Yeah, I mean, I wish you luck. I will say you should always have a sprinkle of like you should always have a sprinkle of. I mean, okay, it's just that to avoid getting disappointed or to avoid like getting too into it, I guess you should always have a little sprinkle of realistic. You know that it might not succeed, but yeah, I wish you all the best to succeed with that. I'm not even sure the genre name. That's how unpopular it is. Yeah. Okay. Well, it's not good if it's unpopular. Or you mean unpopular to make the games? Maybe. GPS game. Yeah. Yeah, I hope it goes well. I mean, I also like. It would be cool if you could have like a game. There has to be some kind of game where it's like a strategy game, because I like strategy games. And it would be cool if you could have like a strategy game that plays out on the real map. And it would be kind of like a global thing or something. Like a fake world where everyone can participate and have their own like kingdoms fight each other or something. But I guess it would not make sense in a GPS form, maybe, I don't know. Even if it fails, I still have a game that I love. Yeah. It's popular to play, unpopular to make. Right. Example of strategy. I mean, basically... basically, so instead of you personally going around... that's the where it clashes, right? I was thinking, like, instead of you personally going around, you have this army that you can send out from where you are, basically. And... you would fight others in the area for territory or something like that, and then, you know, all around the world people would have their local things, and maybe some kingdom grows and becomes like an empire or something like that. And then you had this whole history of the game as well. That would be kind of cool. But then also it's like, okay, well, how much does the GPS play part in that? It's basically just going to be where you're all right now. Maybe you can travel to a different country and start like your own, like you're colonizing or something like that. I don't know. That would be kind of cool. I actually could do that because you can control the character on the screen, but the monsters are your pets, so the monsters aren't controlled in the GPS. Okay. So how does the GPS play into the gameplay? Excuse me. You technically could send them. Yeah. I guess I was thinking more like a strategy, like I don't know, a war-like game. Like you have like armies that you control, or yeah, somehow. Just as a basic example, let's say Risk, for example. And you get like armies every now and then. You get some supply depending on maybe. Would that become like a snowball effect though? Like if you get. I don't know really how it will work, but. No problem. Okay. The problem here is that if you have a stream of values, how would that get serialized without the type information about the type of value that you have? Because here we're kind of assuming that this is a slice of strings, but if you have a stream, how would that get? I mean, okay, I guess. Yeah, the thing is that this slice has to be, everything has to be the same size. That's the thing. And that doesn't work with streams. Streams doesn't have, because right now the stream is, well, I guess it's a pointer though. I guess it's a pointer actually. To a list of values. Yeah, I guess. So the GPS controls your character, and your character control where the pets go. Yeah. That was kind of what I was thinking as well with the war game. Like you can send out armies from where you're positioned. So you have to kind of, or you can like if you send out new armies, maybe that's, you can like travel to a new place and bring armies with you to send out. Okay, but that's that's another thing maybe. Kind of like in Pokemon, you control your character, but you can choose if your Pokemon are in your party or on the beast. Well, to be honest, I'm not that familiar with Pokemon. Actually, I've never played a Pokemon game, so I just know about I know common things about Pokemon. I mean, I know you have these Pokeballs that you capture and you can carry them around. I didn't know that you could have them in your party on the PC. I thought you had everyone with you. Okay, that just shows how much I know about it. Hopefully, at least try them again. What is out? Probably still better than Pokemon. Okay. Well, to be honest, I'm actually not a big fan of those kinds of games. Sorry to say. Like, that's why I don't play Pokemon. It's like I don't like the notion of I have to capture a bunch of stuff. I do like JRPGs. I like Final Fantasy. That's more of my kind of game. When you have, I guess, less. I guess what I don't like about it is like the fact that you get a new thing, then you have to like level it up and grind, and I just don't like the grinding part. I don't know. It's just too much. It's yeah. Technically, you don't have to catch a bunch of stuff. You just have one pet and grows from baby to adult. Like time ago. Right? Yeah. Yeah, I guess. I don't know. I kind of like, going around getting equipment, like upgrading your characters in different ways, things like that. I don't know. The Pokemon never really spoke to me. Sorry to say. I don't know. I don't know what to tell you, but yeah. But I mean, it's obvious. It's very insanely popular game, so that's on me. Okay, maybe we have to kind of think about starting we have to think about allocations anyway, so maybe we have to kind of think about this in another way. Okay, the streams may be a stupid idea. Yeah. I was thinking like, okay, when we have this stream and we could kind of coerce things into variables, but that requires us to know what the value is, and we don't have that type information in the data. So, I mean, we could technically store the type along with the value, but nah. I guess the stream could actually technically. Now, how would this work? We would uncover the stream pointer and then coerce each value. I guess that also works. Because the other way to solve this is basically, okay, well, we're getting all these things, right? And then at the end, we would create one string in memory that would hold every string part and build that up and then return that as the value, like the fully allocated string. But streaming also makes a lot of sense, because we do want to be able to stream other things as well. And then you don't need the allocator. You just need a way to store all these references and then stream out. You don't need to build the full string. You just need to build this array of values that you then turn into a string. You need to make it into a string when you call the executable, or when you want to print. Yeah, when you call the executable. Hello, Kotfi. Welcome back. So if we do want to have this as a stream, we would need to change the executable call to make all the arguments streams instead of strings. I guess that could also be possible. But then also this kind of violates the value part now. This violates values being not allocated things. But it's still copyable though. It is still copyable. I guess the structs are deinitialized, yeah. I wish I could have this so that we don't have to kind of deinitialize this. We have everything in some sort of garbage collection thing instead that we do that with, but okay. Man, yeah, the allocation part is... we need to solve it anyway, so... but yeah, let's try and make this happen here, so... so... let's see, we add this slice here, and then we duplicate that. We serialize everything into this here. Which should... I mean, this is just a stream, really. Except we're turning it into... yeah, we're turning it into this. Man. So we get this list of values, that's the arguments. We allocate that, that's fine. And we get the fit. So this, it should just be a list of arguments or a list of values, right? Yeah, this is a list of values in itself. Where the first value is the list of values. So where do, okay, and then we turn those into a byte string and then store that as a slice. Right, and this is where we need to read them. So the problem is here, we're serializing, right? But it kind of depends on the serialization to have the same... yeah, we're serializing them as slices, right? So... but for a stream, we're doing this, which should kind of make, like, it should turn the slice into a byte stream. Not sure how that works. I think it's just storing then the... it's just storing the, like, the pointer and the length, perhaps. Alright, see you later, Cotfeet. Thanks for stopping by. Also, thank you, Bobinski, for following. Okay, well let's say it's stored as a pointer and a length. Then we should technically be able to get like size of. So let's change this to size of the stream, which is values, slice of values. And we serialize this thing. But before we do that, we actually need to change all the things that are not, all the things that are literal strings into streams. So if we go here and we say, for example, to stream, and we're just gonna make it into a thing. So we're gonna return switch self. If it's a stream already, we just return self. If it's a wait, no, it's a slice. So here we would basically check, okay, well, if the slice is actually we do, okay, the slice is a string, right? We would actually just wrap this in a stream. But then what would this be? Oh, this would, yeah, we don't actually need this. We just wrap it in a stream like that. So if it's a stream, we just return the stream. If it's a slice, we wrap it in a stream, which would now this is the issue here. We need an allocator here actually. Or could we turn this into a slice itself? It could be a pointer to its. No, it could. No. Could it? Can you always make a slice that it's one length? No, because it's a pointer, so it has to point somewhere. We have to allocate that. Okay. Unless we make the stream into union enum. No. Let's just make an allocator. And then this is like allocator error. Actually, let's do stream error. Which is allocator error or unsupported stream coercion or conversion. I don't know what the correct term would be here. Or cast. Unsupported stream cast. So this would be else error or to stream error. And this would be allocator dupe value there we go. Okay. Then what we could do here then is we could say that all of these should be to streamed first. So to stream. Oops. Which needs to be try as well. So we need to wrap this here. So we do that. And then same thing here. Is that we wrap this in a try to stream self allocator. And the error is now we need to add value to stream error. Okay, so now all the executable arguments, the argv is now a bunch of streams instead of a bunch of slices. And actually, this is wrong now. So we need to use, well, actually, no, it's not. It's a bunch of, no, it's, yeah, it's a bunch of pointers to values. However, write all self to bytes. That doesn't really work now because it's gonna include the union enum part, which we don't really need actually. I'm just gonna say if it's a stream, we get the stream and then we write all 2 bytes, or let's do slice as bytes. Stream. There we go. Now technically this actually does turn, like when we do slices by stream, since this is a list of values, we actually do take the type information with us here. So the type information is actually stored now, but whatever. We'll have to figure it out somehow. Okay. I wish I could do it now, but I just don't. The allocations thing, well, or the stream thing is kind of... It's gonna come forward at some point. We'll see. Okay, so now everything is stored as a stream there. And there we go. So now when we evaluate the call, instead of interpreting these as slices, we actually need them to be streams. So we will say that this is a stream now, and we deserialize a stream instead, which has to have now a special thing. So this would be stream wait, how does this doesn't work? This has to be like a this has to be like this. What the hell? How is that not an error? Okay, anyway, the stream, yeah, because if you do this, yeah, that's weird. Okay, so the stream is gonna be, oh man, what the, no, yeah, that, okay, we just take take an array that is the size of this, and we will. Can we just take can we just do pointer cast here? There is a thing called like slice, no, bytes as slice, right? Okay, let's do that instead. Okay, so we get this stream here now, and we need to build up the org now. So let's create org buffer, and then we'll create a org writer. And then we'll loop through org stream.stream, and then we'll say deserialize. Wait, that should exist. Oh, right. So it's gonna be like value deserialize. Actually, no, wait, we don't need the DC. We have the value. Okay, but now the problem is like, what is the value? So actually, we need to like, we need to have a function that kind of creates a string out of this, materialize string or render string, whatever we have. So this would be like, I'm gonna say self materialize string, something like this, and that's the value, and then we materialize it into a writer there, and there we go. That should be it. Now we just need this function here, and then argument is gonna be, instead of slice, it's gonna be the actual. No, we don't get the slice. What we do is we do arg writer buffered. That's the argument. There we go. Now we need this materialized string. So we need the value and the writer, and it's going to be some kind of error void. All right. So we need to switch on the value. If it's a string, we kind of need to do the same thing again. Let's copy this part, put it over here, and then you are a buffer, you are a writer, you are a stream, whoops, and we recursively call materialize string with the writer there. Then we have, no, we don't do this. or we do, or we don't, or we do, or we don't. Actually, no, wait. No, I think we just pass this along, actually. Yeah. It kind of sets like a hard limit now on these strings being like 1024 long, but yeah. Where are the compiler errors? I swear there's gonna be a whole bunch of compilers that we're missing out. If it's a slice, I think what we do then is basically we just return the slice. Like if it's a slice, we have to check, like, is it a byte slice? We just return that. Otherwise, I don't know, man. It could be a byte of streams though as well. We don't really know. That's the thing. Like, let's just check if it's a byte slice. So if this is 1, well, if it's not equal to 1, we return an error. Material string error unsupported type. Let's also do allocator error. Hello, Hanso. Hi. May I ask a question? Go ahead. Welcome. I assume you know how to design systems, solve business problems with 10 years of experience. What makes you go to game development? I mean, I've always wanted to get into game development. It just never happened, I guess. And I don't know, I just like games and making, like, or trying to make games, or think about ideas for games, you know. And then you know, it's kind of like I always had this you know, different ideas that I wanted to make and try and play, but you know, it was very hard, so I never got to. I've tried again and again to actually make games, but yeah, it's pretty difficult, and I basically just, after a while, I get stuck and I lose interest and start something else, basically. And also, it's like I like variation. I like exploring new things. So after 10 years in like web development, I feel like, well, it is constantly changing, but it's still like the same anyway as well. So it's like, yeah, that's basically it. I want to explore other areas as well. Like right now, I'm still working with, you know, web development and all that, but I like to explore other stuff as well. So I'm always like, I've always explored different areas and new areas for me to explore, just as I'm doing now with this programming language here. So that's basically the reason. Is there a particular reason why you ask? Material string, right? So we recursively call that. If we get a byte slice, we will get the string as. So we do like get slice. Yeah, we'll try to get it. that would return, that would give us the string, and then we will do write all string. All right, pretty nice with a writer here. Take int can now be an error, so there we go. Or it is an error actually. Yeah, there we go. Now we get errors here. Bytes as slice. So expected type found a line 1. Right. Like, I'm not sure what you could do with this align. Like, can you just align cast it and then that's fine? Or do you have to do something more here? Yeah, I kind of get it. I was a Java developer for 1.25 years and then a data engineer for 1.25 years. Now I'm going to try to pivot to DevOps, see the bigger picture and learn this to design systems. Okay. Cool. Yeah. Yeah, I mean, it's like when you're doing something for really long, you just, I don't know, for me, I just like to explore different areas. And I mean, don't get me wrong, like web development can be a lot of fun as well. It's nice, it's cool that you can actually get the skills to build whatever system you can think of, basically. But yeah, it does get old. I mean, I've never liked doing the same thing over and over. Like, I've never liked that. Like, you know, that's why I quit playing WoW all those years ago. Like, I'd never liked the grinding part. But yeah, you can make a multiplayer game. That would be cool. Yeah, I would like to maybe sometime. I don't know. But then also, like, I just like programming as well. I just like making stuff with, like, I don't know. I just like learning how the computers work, and going low level as well is one of the fun things for me. And learning how things actually work, like to be able to deep dive into that and maybe create something, you know, with that experience. So, you know, I've delved into the assembly code and make things like that, make my own like compiler that compiled to ELF executables directly without using any tools or libraries or anything. So that was really cool experience, because you learn a lot about how the computer works and how the CPU works and everything like that, and the memory and everything. So yeah, I just love everything that has to do with computers. Almost like, but yeah. And but really I just love making this like languages as well. Like this part here is really fun for me. So yeah. And making games, like, yeah, I find it like it's fun and educational, but it's also very challenging. And there's so many different areas that you need to learn before you can make a game. Like, there's graphics, there's sound, music, you know, programming, you know, there like maths. There's like all these different areas that you need to kind of learn a little bit in each one. And then also like game design and animations and you know, all different, like graphics, programming. There's like so much you need to learn before you can actually make a game at all. Like, so it's very challenging. And I feel like making a program language is like easier. So yeah. I only say Zig or C++ as a way to get into kernel development. I thought about that. Like, I recently looked at one of those Linux from scratch guides, and I tried to like install Linux from scratch, which is kind of like you're kind of building what you need to do is just what it means is basically just compile the kernel, and perhaps also compile, you compile a bunch of things that you need for compiling the kernel, but also some tools that you're gonna have, like the most basic tools that you need, and put it on a virtual machine. Basically, that's what I had to do, because I don't want to deal with all the dual boots or anything like that. But maybe I will. Maybe I actually buy another hard drive and dual boot with Linux or something. But then I would probably use a distro or anything. But while the point is that I'm trying to make is, while I was doing it, I kind of felt like, hey, we're compiling all these things with like C, and like an ancient language. I mean, it still works, of course. I mean, yeah, but it just felt like, okay, why? You could probably just start to change this to Zig. Because Zig can compile C, right? You just have to provide the correct flags and everything. Well, you have all these make files in the packages, right? So you have to have the correct flags and all that, but the configure scripts and all that, I wouldn't know firsthand how. I wouldn't know like where to begin with that, but it just feels like it could be a lot simpler. Like imagine making the kernel with Zig instead. Yeah, that would be kind of cool. Like making an operating system with Zig, based on Zig. Like maybe someone's already doing it, actually. We have the Zig Discord, and you have like projects here. Yeah, you got like OS Dev. Like there's an OS Dev channel in Zig. I don't really look there much because I'm not really into making operating systems. It would be cool to try. I did try once, but it was hard. But there's probably people doing that right now, actually. And then you can look at writing an OS in Zig. Yeah, I don't know. Anyway, it would be kind of cool. Also, if you wonder how far I got into the Linux from scratch thing, it's basically I got to the point where you need to run the tests for, I think, either GCC or glibc. I don't remember which one it was. But you run the tests, and then you get like some expected failures and maybe like 2 or 3 expected errors or something like that. I got like 160 errors, and then I just gave up. So that was not a nice experience. I just wasted a whole bunch. Well, I didn't waste it. I kind of meditated in between there. But yeah. Anyway, this thing. How do we solve this here? Given a slice of bytes, return a slice of the specified type backed by those bytes preserving pointer attributes. If t is 0 byte size, the return slice of a length of 0. Okay. Returns the next n bytes from the stream as an array, filling the buffer as necessary. And And we can't take these as structs because they are... Well, actually, we don't take those at all. We take this thing here. Wait, couldn't we just take this? No, we can't. Is there like take value, take... there is take enum. But that's not what we need right now. Take... God damn it. Struct pointer. Could we do a line cast? I don't know. Let's try it. It might blow up here. I have no idea how that works. Okay, well, whatever. No field or member function name deserialize in built-in type union field. What? Oh, I see. So we would need to take like type here and then deserialize, I think, yeah. Expected 2 arguments, found 1. Oh yeah, we need self, so this would be T. Expected use size found tag type. Oh. Is it the adder? Maybe adder. So adder would be adder take int. Yeah, this would be the same thing actually. Another one. So what do we got? Use size, slice, structure. Expected use size found. Why do we get this now? C3. Is C3 good? I wish it would say which one it is. Wait, how did you get not type name, it's no. Wait, how did you get a tag name? That's not tag name. One second. What? So it's the field info of the value with T. That should be the slice, the type. So that should be the slice type. Then we call deserialize. Wait, the slice, but the slice is not a. The slice is. It's not a thing. No, wait. This doesn't. This. What do you mean expected 2 arguments? This is weird. Deserialize. Function declared here 92. Element size. Oh, okay. I see. So, okay, the slice is not meant to be deserialized through the value. And that actually is an issue right now because that means we can't actually call deserialize using this here. Well, I mean, yeah, so if it's a slice, we get an error. That's what we get. We get deserialize error, unsupported, deserialize. Yeah, that's what we get. What else do we get here? Reader error. Three arguments. What? Oh, the struct? No. Yes. Okay. Yeah, the struct doesn't work either. So struct. There we go. And execode has no memory call deserialize. Right, exit code. Deserialize. Can we get this? I mean, I guess we just read this here. We just read this. Does this work for union enums? Tag type. It just takes the integer. No, that doesn't work. Like, why isn't there a tag like take union enum? Why does that not work? Okay, let's just do the thing. Let's take array size of this querycast or something. I don't know. Wait. Pointer cast dereference. Now this would be no, this would be align cast standard memory bytes as value. This right? Found exit code. Oh yeah. Right. So deserialize. Oh shoot. Okay. Well, let's do this. Exit code, and then exit code. Deserialize, and then we do. Just because I don't want to have... Okay, there we go. I don't want to have to refer to this value in the, like the IR in the exit code type. Expected unit type found... Exit, what? Oh, wait. Oh, that should be an error. Yeah. There we go. Okay, here we go. Will this work? What the hell, man? Given a pointer to an array of bytes, returns a pointer to a value of the So if we deref, we copy it, right? Good. Now what are your issues? The error. What is it? Value deserializer. Unsupported type. Oh, materialize string. Yeah. But this is the value. Switch must handle all possibilities. Okay, so now we're back here. We do have some weird thing going on there, but okay. So if it's anything else, I think. Well, actually, if it's like a U integer, we can coerce it. Also, an exit code. Now, okay, so we have a couple of different groups here. So U integer would be print. that. And then we have another group, which is going to be inline. And yeah, this is going to be formatted. There we go. Now we got other stuff. So what else do we have? Void. It's gonna be nothing, I guess. Structs. We're not gonna do. Address. I guess we could do address maybe. Actually, address is different. Address is like. Let's do that. What else? We have void, struct. It's gonna be nothing. Okay. This doesn't even have an error, I don't think. Or is this error here? No? No, it's this one. Yeah, unsupported. So let's actually just add get slice error. Actually do this, so we can do that, we can do this, I think, or maybe this, get slice error, and rate failed. Yeah, I like having the errors very explicitly, because of the fact. Yeah, because I'm not gonna explain it. Okay, now we have some kind of weird issue here. Exact division produced remainder. So where do we have that? I think in here we have like div exact somewhere. Oops. We do have div exact, but it's not well, this is not comp time, so. Deserialize 257. Bytes length size of t. Bytes a slice. Take array size of pointer to value. Bytes a slice. Wait. What are we trying to do here? We're trying to get a stream value. So we're taking an array of this many bytes, and then we're trying to make it as a slice of values. But that doesn't work here, because this is this is supposed to be okay, this is supposed to be, I'm just gonna try and cast it actually. No, that doesn't work. It's not casting, it's more like, what the hell is this? How, like, It's more like I need to construct a slice, the pointer and the length from this array. Not sure how you do that. Zig construct slice from like the thing is, this array describes the slice itself. It doesn't describe the contents of the slice. It describes the pointer and the length that we need to make the slice. So this would be more like bytes as value, and the value we're trying to construct is this. And I guess we dereference it. Okay, now I have no idea if this actually works. That's gonna be, yeah. We're gonna see, but okay. Now we get this stream, right? And I guess we can just materialize that directly. We don't need to loop through the stream itself. We can just say, well, this is a value, so we can just say materialize string on arg stream itself. There we go. And as you can see here, the limit on all the strings right now is like 112,024 for arguments into an executable call. But hey, and now we're also, this is kind of, this doesn't work here. We need to duplicate this. We're adding this buffered here, but this buffer goes out of scope here, so we need to duplicate it as well. Maybe we duplicate it here actually. No, we don't, because we use the writer. That's right. Maybe we can use, actually maybe we'll use an allocating writer actually. Yeah, let's just use an allocating writer. So allocating, and we initialize with the allocator. We don't need a buffer, and here we do toOwn slice instead. Okay, there we go. So now we're doing that. And then you would be writer. We need to try. All right, I think that's it. So we are actually, now we have the stream and we have a way to materialize the stream. Now it's kind of janky a little bit. We're not really consistent with how we store values in the thing. Like streams are very special right now, but whatever. So will this work? Or will it crash incredibly? How many bytes are we using? 400. So it basically doubled the bytes here for some reason. Also, why does it just say echo here? I guess this is this one here. And then we get the stream here. 0. Where's the 1? Should have a 1 here somewhere. I don't know. Okay, whatever. So we have these things here. We got a couple more instructions, or maybe we don't. Okay, so we still crash. We crash at this first call here. And we're getting a slice of address 9, element size 16, length 4. So here you go, 16. That's a slice length, slice size. 8 bytes for 8 bytes for the address, yeah, 8 and 8 bytes for the length. So that's I mean, do we really need 8 bytes for the length? Okay, well, whatever. And then you got the length here, 4 of those. Does that make sense? 1 for this? No, wait, 4? That doesn't make sense. Okay, we got segfault at address 0. Very interesting. Okay, this doesn't make any sense. Stream, for stream, try material string. We got a segfault here. Oh, segfault here. We're trying to access the stream. Okay. So it could be something weird with the whole things. With the whole thing. Welcome back, Penguin. Alright. Probably have to go here pretty soon here, but let's just see if we can figure this out. So it's probably something to do with these things. So I want these here last here. Actually, I want these above format so we get the same order. There we go. Serialized stream. Bytes as value. This is the value we're trying to make. No, wait, what the hell is... No, this is deserialized, yeah. Yep. And then serialize, we'll write the slice as bytes. So could it be something with the alignment? It like pads a bunch of zeros in the start or something? I have no idea. I thought it padded at the end. Yeah, when you create slice of bytes, I don't want to have the padding. Preserving pointer attributes. What if we change to... Nice addresses here, or bytes, or okay, whatever. Array of U16s, slice as bytes. Expect slice length equals 4. Makes sense. And okay. Packed struct. Maybe we'll make it packed. foo undefined slice of byte. Slice as bytes as this, but it's undefined. What? So the address of foo, we're converting that to a pointer to a list of one foo array. Okay, and then we're slicing that 0, so we're taking, but it's undefined though. Okay, and then we set 0 to, so we're basically creating a pointer to foo, except the pointer is like a byte pointer, and then we're setting the first byte to 13. But since it's packed, this would correspond to these things here. Interesting. Maybe it will magically solve itself if we just make it packed. Could you make a packed union? What other implications would this have? I don't know. Packed unions don't support enum tag type. What if we made these like this? Does that work? Okay, I get it. But okay, what if what if this was packed? I don't know, man. Okay, let's do this. We'll do that. Before we do that, wait, slice as byte. No. No. That is not correct. This is not correct. It's taking the contents and putting them out. No, that's not correct. That is not correct. We want to write two bytes. Yes. We want to write this value as a byte. Okay. There we go. Does that work here? Okay. There we go. Hey! What the hell? Okay, that just works, I guess. Except for this part here. It doesn't really work here. Yeah, we get like 2D and this address. Cool. So that's what we get over here. So we push that's the first one. Let's see, line 3, yeah. We set something here to, no way, yeah, we set it to 1 and then we're done. We jump to after, so now we're here. We create the executable call context. We set that. Okay, and then we call, wait, we push this. Right, that's a context, yeah. Then we call, so this is something that's referencing the stack here. So we call and we get some slices. So this is the arguments slice, which is a slice of slices. 2 slices makes sense because we have echo and then this one. Then we get another slice, address 41, that's the echo. And then, are we done? What the hell? Okay. Right, we call and get sliced, that's what we're doing there. And then we have the stream, right? So we should, but that should, no, that's not the, okay, you know what, let's do this. Let's do, like, once we've done this, let's log this out. Argument, this is that, which is gonna be argwriter written. So arg0, what? Oh. Oh, I see. I need I here as well. Invalid format. Oh, god damn it! I'm mixing it up. Okay. All right. Arg0 echo. Arg1 is hello. Arg1 is this. So there we go. There. Okay. How does that happen though? So we go in here, it's a stream, right? And we're going through each thing here to materialize. So let's get some more debug information here. And we're gonna say stream so that I'm gonna do T because it's a value, right? So, or we could actually format it, try to format it there. Oops, I did the same thing. Okay, so arg0 is echo. Yeah, here we can see that this is a some kind of slice here, which goes from 0 to 4. This, wait, or it I think it starts at address 0 and then it goes to, it has 4 length. So really this should be like dot dot and not colon actually. I just, yeah, where's the format slice? Where's the slice format at? Are you slice? No, you're source. Set, jump. No. Where's the slice? Here's the slice. Okay. You should be dot dot. Actually, you know what? This should be actually be length plus address. Actually, let's just add plus here so that we can see it's kind of, you know, relative. Yeah, let's do that. Whoops. Stream. Yeah, so now we can see like, okay, well, it goes from 0 to +4, 4 plus 5 with, so it means like 5 length. And this is the same thing. And then here, this is just 2D. What is this? So let's do the tag as well. Slice. Oh, this is an adder. Okay, I guess if it's an adder, we can resolve it instead of... I guess we dereference the adder, maybe. Yeah, let's just do that. Adder. Yeah. So this would be, actually, yeah, let's do this. Let's do that. And we actually want to do try materialize string or self-adjusting. The value is going to be resolve value t, or actually resolve value you know what, we could just do resolve value is resolve value and we'll do it on that one instead. So we're kind of dereferencing it before it gets in here. All right. And now we can keep this, I guess. Try, please. What kind of error do you have? Everything? What kind of error do you actually have? Do you have any error? You don't have an error. You don't have an error. We have this error here. So that's just, okay, let's just do this. Resolve value error. It's gonna be error. Unsupported resolve value type. And this is resolve value error. There we go. And then you are also resolve value error. And now we should get some errors somewhere. No, maybe not. Okay. Actually, we can remove you. Now we got a no. We got a 1. Still address. What the hell? Unsupported, okay. Oh, where's the material string? There we go. Oh yeah, okay, yeah, it makes sense if it's an address, because we're streaming it, we're showing it there. So actually, let's just move this over here and materialize string instead. And this is value now. Actually, let's move it here. Let's do resolve value. There we go. Alright, now we can see. So stream. Yeah, and then we got a slice. Another stream, one slice. Here's a stream, we get this slice there. And there's the error. Oh, okay, maybe we're trying to resolve a stream and it fails, perhaps. No, it should just do else or value. What the hell? What is happening? Oh yeah, sorry, because it's like, okay, it's showing the when it's like down there. Okay, so this is like before resolve, and this is after resolve. Here we go. Before resolve, after resolve, we got a stream. Before resolve, we have an address of 2D. Right. So the problem, I guess, would be we just get an address. We don't know the type, perhaps. Like when we compile a literal, which is the integer, right? We just get the thing directly here as a value. And then that is stored as, like, if we have this part as of an if, that is stored as a ref, I'm pretty sure. But why would that be part, like, why would that, well, is it even the if though? 2D? No, it has to be like the string literal, yeah. So, okay, so we're adding the text. No, it's this one. We compile the expression. Now this should become this should just be the integer. It should not be an address. I don't really understand why it becomes like an address. The thing is, like, the n will be an if with an else. We store the result in a ref, and that's what we return. We return the ref location here. That is then stored in the binding. So we declare the result is stored in the binding. So this should now be a ref. And then when we look up that from like identifier, we should get the result out. We should get the ref out. Why do we get like an address? I don't wait. No, wait. No, because when we call this, we turn it into the address. Right, so we need to map it. Yeah, we need to map the thing. But why? But no, wait. Welcome back, Penguin. Okay, I think this might be a problem of the string interpolation part. Like because when we store it at an address, no, because that's a ref, and we can get the value from the ref. Yeah, so evaluator, materialize string, resolve value, we map the address. If we get a ref, we should just get this ref here. Why does that not work? Map adder map adder, and it's gonna be ref. No, not ref. This is read only. Wait, how did 2D become? No, that doesn't make sense. Oh, that's the text part, I believe. Okay. Okay. I think when we get to the ref part, it won't actually be an error. It's when we resolve the 2D, which should be like a read-only thing. That's when we get this issue. So what's happening is, I think, where's the thing? The if, no, not the, no. No, it's, yeah, it's string literal. So this is empty, let's say. This is empty. It's just turned into an address of the read-only, but the read-only doesn't have the information about, it doesn't have information about the slice. Why am I doing it like this? This should be Add slice. This should be add slice, not add whatever. Yeah, and it's a string and the data is text. There we go. Okay, there we go. Hey, hello, one, yes, okay. All right. So now with these like internal stream things, we can actually interpolate as well. Awesome. And we can have as many as we want. N is equal to N. Cool. Okay. I still feel a little bit iffy about these streams, but yeah, it's fine. It's nice that they are basically arrays that you can just loop through them, so we don't actually need to allocate anything. When we produce this string, we just iterate through the segments and materialize them as needed. And we could even have, like, let's say n+1 here. Actually, we can't because we don't support arithmetic right now, but because I didn't prioritize that. We could easily add it though, but I mean, yeah, technically we could add another string here, n is really equal to n. Oh, we got a 1. Can we do this? No. What's the issue here? Oh wait, it's this part. Why did that get there? Okay, that should be work. That should work, yeah. And then just this work. I think it should work. Okay, it doesn't. It works, but then again, it also doesn't work. Okay. There we go. Interpolations work. Awesome. Okay, but I think that's gonna be it for this time. The IR. Do I have a section for IR over here? I don't think so. Maybe I need another to do IR to do here. So we have like the compiler, validator. We have, what would you call this? Like the backend? No, the data maybe. Instructions. I don't know. We'll fill this out a little bit. I don't really have anything here right now. Compiler. Like instructions, we have like the basic structure. Compiler, we don't have like arithmetic. Arithmetic. And Boolean algebra. We have basic executable calls, but we need to support, of course, pipelines. So we need some kind of pipes data. Pipes. We kind of have streams. We have, you know, unsigned integers, strings as slices. Oops. We have, I guess we have void. We have exit codes. Exit code. What else do we have? We have address. Oh yeah, we have structs as well. There we go. That's all the values. What else? Instructions. Yeah, that's right. We also have like instruction address, labels, address mapping, oops. We have like push, stack push, stack pop, arithmetic. I mean, I guess we have the basic structure of arithmetic. Compare, logical, new ref, that one we have. Set address to value, we do have that. We have jump. We have unconditional jump. We have conditional jump if true. Condition of jump is false. We have call, executable, and we have exit as well. All right, Borchek, you're living on borrowed time. Oh. I'm just writing down a little bit here. I'm gonna end here, but I just write down like what we have right now, what we need in the foreseeable future, just what I can think about right now. The evaluator. We also need like the runner. Actually, the evaluator is, yeah, we need like, we have like execution context. We have like read-only data, which could be shared between threads. We have the instructions, which also could be shared between threads. We have the stack. This is per thread. We have refs, should also be per thread, question mark. Like there has to be some kind of common memory area, right? That you should be able to like return something from a thread to something else. Like they should be able to produce something that could be used in another thread. So that maybe the pipes could be that. Maybe the pipes could have a way to communicate between the threads. I'm not sure actually. But I think the threads, the refs right now should be per thread, because that's kind of like a local address thing. Perhaps. Yeah. Because these two kind of are the same thing. Like the stack and refs, they are kind of the two sides of the same coin, you could say. What else do we have? Let's go to the IR context. We have, we're storing the labels, of course. And all of this we do have. We have struct types as well. Those could be shared as well, of course. I mean, technically, actually, one thread could create its own struct types at will. So really, maybe they shouldn't be shared. I don't know. Let's add a question mark here, because technically, any thread could execute code that will create a new struct. Or could it actually? Maybe it couldn't. Maybe it's maybe that's semantics. No, yeah, let's have it shared. Yeah. I'm not sure actually. I don't know. Stack refs labels. That's it, right? Instruction counter. That is per thread, of course. Labels are shared. Let's actually do this. Let's do like shared between threads. It's gonna be these, and then per thread. There we go. We also have the stack counter. Wait, do we have the stack counter? Yeah, the stack counter is like built into the array list, so. Instruction counter, refs, stack and the refs, yeah. Alright. What's missing though is the actual threads. Threads. That's what's missing there. Threads are missing here, but we can step through step instruction step. That we have. And we do have the call executable. We have materialize string. Yeah, materialize string, which is like streams, slices, unsigned, integers, dereference address, and then the rest is, yeah, we'll see. Okay, what we don't have is execution results. Or do we have exit codes? Yeah, we have exit code, okay. All right. What else do we have? We have new ref. We have set. We have jump. Push pop. Push pop. Call. jump, ref, set. Oh yeah, and exit. Okay. Everything you need. All right. Cool. All right, so yeah, I'm gonna have to plan it out a little bit and think about how to. I think the next thing we're gonna jump on is the pipes. That is gonna be a huge thing. Like, yeah, I don't really care about this. This is so trivial that I don't want to deal with this right now. This is very trivial thing. This is what we need to deal with. Because it's kind of like the MVP right now. It's like, okay, well, can we get pipes to work? Can we get them to work with threads? Yeah, so what we need for pipes is like threading, like the virtual threads. We need the pipe. Maybe I'll start work on a debugger as well. Because of, you know, the complexity is kind of ramping up a little bit. So it will be cool to add a little bit of debugging as well, that like a step through thing that shows like the current status of things as well. That would be kind of cool to build as well. So yeah, so the pipes are going to be what we actually need to, like, if we can implement this in an asynchronous kind of way, a streaming way for all the pipes between all the processes and stuff. That's gonna solve like all the issues basically, and from there we can just build on there. So this is the problem we need to solve in order to kind of prove that this IR thing is worth it here. And from there we could build everything else basically. So yeah, that's gonna be that. Also the structs, we're gonna need to kind of map them to the types of the type system. The type system isn't really part of this right now. We don't really use that. The structs, I kind of made my own. I kind of made the own, like the IR has its own version of a struct type right now. So we have to be able to bridge that a little bit. Maybe even just use straight up the type expression struct instead. But there's no way to create structs right now anyway, so it doesn't really make sense maybe to use that. That's when the type checker will come in. But I think what we need to do is prove that the piping could work, and then we'll worry about everything else. So that's going to be the next step here. I just wanted to do the interpolation first because, yeah, that also felt like a little hurdle to get through. I'm not even sure if we're gonna need an allocator. Well, of course we're gonna need an allocator. We need an allocate. We need to allocate. We need to garbage collect. Yeah. I was thinking like maybe we could use stream somehow, but yeah, we still need to like garbage collect. We'll see what happens, but yeah, the pipes is gonna come later. So anyway, this is gonna be it for this time. So thank you very much for joining and watching me and chatting with me here, and I hope you all have a nice day, and I'll see you later.